Welcome. If you're returning after learning the basics with us, we're delighted to have you back.
And if you're just joining us for the first time because you already know the fundamentals of Python, like if-else statements, for loops, and strings and lists, then welcome for the first time. Just be sure that you watch the video introducing the Runestone textbook environment because we're going to be using that throughout the course.
I'm Paul Resnick.
And I'm Steve Oney, and we're both faculty here in the School of Information at the University of Michigan.
In this course, we're going to cover the rest of Python fundamentals, still focusing on the execution model to help you reason about and debug your programs.
We're also going to learn how to read and write files. We'll learn about the Python dictionary data structure, and we'll learn to use the accumulation pattern to accumulate results from complex data structures and to accumulate results into dictionaries and from dictionaries.
You're going to learn how to define functions, which I think of as the dividing line between just playing around with programming and becoming a real programmer.
And we'll delve into some of the subtleties of functions, including optional and default parameters, keyword-based parameter passing, and anonymous lambda functions.
And you'll learn about sorting. You're not going to learn sorting algorithms, but you'll learn how to use Python's built-in sorting capability. You'll pass in the right parameters, and you'll get your items back in exactly the order that you wanted. The final project will be a little sentiment analysis program. We're going to give you a pile of fake tweets, and you're going to write code that counts how many positive and negative words there are. You'll write out a comma-separated values file, upload it into a spreadsheet, and generate a graph so that you can analyze. Do those tweets that have more positive words in them get more replies and more retweets?
Sounds fun, and that's also going to synthesize all of the things that you learned throughout the course. Now, like the first course, we're mostly going to do screencasts with code examples, but we'll occasionally come on screen for words of wisdom and to introduce topics.
I'll also be telling a few more dad jokes.
So let's get to it. Bye for now.
Hi, everyone. I'm excited to show you some useful features of the free interactive textbook that will be available to you as part of this specialization. Content in the first 4 courses all track pretty closely to the textbook content, so whichever course you're starting with, you'll want to go through this video to see the important interactive features. You can skip it if you've already seen it in a previous course. The Runestone interactive textbook environment is the brainchild of my friend Brad Miller. I've made a few contributions to both the software environment and especially the textbook over the past 4 years, but Brad deserves almost all the credit. Let's take a look. The first thing you'll need to do before accessing any of the textbook pages is to log in from Coursera. So I just click on this Open Tool, and I'm automatically logged in. You've already logged into Coursera, and Coursera is passing the credentials to Runestone, so you'll be automatically logged in here. Once you're logged in, all of your work will be saved, and we've deliberately disabled any other ways to log in except by doing it through Coursera. So when you first log in, following that link, you'll be taken to this practice page in the textbook. It's our way of encouraging you to use the practice feature every day, but we'll come back to that later. Once you're logged in, you'll be able to click on any of the links for the readings, and you'll be taken directly to the pages in the textbook for those readings. So here's a link to the Runestone page for variables, and I'll click on it. And now I'm on a textbook page. In the textbook, you'll find text and images, diagrams, but you'll also find some interactive elements. For example, here's what we call an active code window. It's got some code in it, and I can click Save and Run. It'll run and print something out over here in an output window. I can change that code. And I can run it. And all of your code versions, when you save and run them, will be saved. I have this little scrubber here, and I can move it, and I can see all of my old versions. And they're not just saved while this page is open, they're saved permanently. For example, let's reload this page. When the page loads, we're back to the original window contents, but I can click Load History, and then I get the scrubber and it shows me my last code run. Now if I rerun a previous version, it won't show in the scrubber as being the latest version, but if I change it, instead of 17 I do 18, now it becomes the latest version in the history. Show in Code Lens is a really useful feature of Active Code Windows. This is an amazing tool developed by Philip Guo, a professor at UC San Diego. It lets you step through the execution of a program one line at a time. I can click forward, and it'll just show me what happens after one line is executed and the next and the next. I can print out just the first message, and so on. That's not such a big deal now, but it'll be really useful for you when you start to do more complicated programs with conditional execution and iteration and defining your own functions. Part of our educational philosophy in this specialization is to reveal all the magic. We want to give you a way to reason about how your programs are executing, because that's the foundation for being able to debug your code through understanding rather than through trial and error. Code Lens really helps with that. Now sometimes these Code Lens examples are built right into the textbook, but you can always get to Code Lens by hitting the Show Code Lens or Hide Code Lens for any active code. So here are some that are built in to that textbook page. There are also other interactive features. Here's a multiple choice question. You can answer those and get immediate feedback by clicking on Check Me. I've actually already answered this one, but suppose I said Thursday as the thing that would print out here because day is set to Thursday. I click Check Me, and it gives me some feedback. It's true, Thursday is the value of day, but it gets overwritten later. So the correct answer is 19. Now when you get to the bottom of the page, I suggest that you click on Mark as Completed. If you haven't clicked on it, this is what it'll look like initially. If you click on Mark as Completed, a couple good things will happen. One is you get the satisfaction of it says, yay, completed, well done. But you get a couple other things too. First, some of the multiple choice questions or other activities on the page get added to the practice tool, which I'm going to show you in a minute. And that practice tool will help you review things so that you don't forget them. Sort of like vocabulary flashcards when you're learning a foreign language. Second, the pages that you've marked as completed will be marked in the table of contents, so you can keep track in the textbook of what you've read and what you haven't. So here's the table of contents. And you can see these orange dots indicate things that I've completed, or I've marked as complete, and the check boxes, the check marks indicate things that I've opened but I haven't marked as complete. So this completed button at the bottom of the page, it's separate from marking a reading as complete in Coursera. You may want to do both of those things. In Coursera, we'll generally provide you with links to particular pages, and so you can just read that one page. But if you want to, you can navigate through the textbook once you're on the Runestone site. And we have these forward and back buttons. This goes to the next page in the book, back to the previous page. If you click on the textbook title, as I showed you a second ago, you'll get to a table of contents that's very detailed with every single page and sometimes subsections within the pages. If you want a more overview look at it, you can click on this chapters and it'll show you the different chapters, and you can just see the detail for one chapter at a time. Now notice that the orange dots aren't shown on this detailed view of just a single chapter. That's a little unfortunate, and now that I've noticed it, I'll try to add that feature at some point. Finally, there's a search option. So I can search for variable, and it'll tell me lots of pages in the textbook where the word variable shows up. There's also an index. If I want to look for various things, and I can click on them, and it'll take me to where they are in the textbook. Normally, if you log in from Coursera, you'll be taken directly to the practice feature, but you can also get there from within the book by clicking on Practice. What this practice feature does is it re-presents to you questions on topics that you've marked as already completed. That thing at the bottom of the page where you mark the page as completed. When you're here in the practice feature, you get to answer it again, and if you get it right, it'll remember that, and it won't ask you that same topic again for a long time. If you get it wrong, then it might ask you again tomorrow. So this practice tool is the brainchild of my doctoral student, Iman Yekizare. He just implemented it last year, and in the first semester where we made it available to students in our on-campus classes, those students who used it in the first semester where we made it available to students in our on-campus classes, those students who used it more did a lot better on the course exams than those who didn't. It was a pretty striking result for me because I'd been monitoring for several years to see whether just spending more time in the textbook had a similar effect on student performance, and it didn't. Now, in my on-campus classes, use of this practice tool is now required and earns a few points towards the final grade. For the Coursera courses, it's not required, but based on the results I've seen with our on-campus students, I strongly encourage you to use it a little every day. I think you'll also find it rewarding. Our on-campus students love the fireworks that they get. So here I'm going to answer a couple of questions. I have only 2 left to practice for today. And I'm going to say, done, ask me another question. And it gives me one more. It says, hang in there, last question for today. And what's going to print out? Oh, this is a review, the one we just looked at. I say, check me, and then I done. And I get these fireworks, which are a little fun when you finish all the questions for the day. Oh, where's the... Okay. For those of you who are taking this course for a certificate, you'll also see links to graded assignments, usually at the end of each lesson or set of lessons. In the first 4 courses, the assessments and projects are in the Runestone textbook and they're all auto-graded there. You'll only be able to see these in Coursera if you're paying to take the course for a certificate. If you're not paying, you can find similar questions in the end of chapter assessment pages in the Runestone textbook. So let's follow the link for this first assessment. And this assessment just has 2 questions. I've actually already answered one of them correctly before. That was a multiple choice question, and they want me to write some code. The answer to this one is print hello world. I'll save and run it, and I get some immediate feedback. There's an automatic test in here, and it's telling me that I got the right output. If I said hello world instead, I would get feedback saying that I had failed. Now it actually, when I tell it to grade me, it'll use the best answer I've ever given. So if I ever manage to pass the test, I will pass this. We've set up the assessments so that usually you have to get 100% in order to pass the assessment, but you can keep trying and keep getting feedback until you get that 100%. We've done that because we think it's really important to master the early material because things keep building on each other. So I click Grade Me, and it comes back. You can see now that it's updated the score to 1 instead of 0. I've gotten a total of 2 out of 2 for this assessment. And if I go back to this page on Coursera and I refresh it, it'll tell me instead of trying again, it's going to tell me that I've passed. Passed with 100%. That's the Runestone environment. It's been a labor of love for all of us who've worked on it as an open source project over the last few years, especially Brad Miller, who started the project. I hope you'll find it really helpful to you as you master the fundamentals of Python. I usually end my on-camera segments with a little joke, so here's a bit of humorous advice. Procrastinate today, always today. Don't put it off until tomorrow. Okay then, don't listen to my advice. Don't procrastinate today. Go get started with the first lesson in this course. I'll see you next time. Here we go with processing files. Up until now, the only data that our programs have processed, the only inputs, have either come from literals that we put into the program itself, or things that the user typed during execution as a result of a call to the input function. The only place where outputs have gone is the output window, which doesn't persist after you go to another page in the textbook. A file contains data that persists between executions of your program. As a computer user, you're already familiar with the concept of files. You've probably worked with image files and spreadsheet files and word processing files. In this lesson, you'll learn how to manipulate files in a Python program. We'll only be working with text files, not audio or other binary formats. At the end of this lesson, you should be able to write a program that reads a file's contents, either as a single string or line by line. You should be able to use relative paths to specify the location of a file. You should be able to write new text to a file. We'll see you at the end for a wrap-up and more geeky humor. Welcome back. What is a file? It's just a collection of data saved on a hard disk or other storage that persists over time. A file has a name, and files can be organized into folders or directories. We'll be working with text files as opposed to images or sounds or videos. Here we have an example of a file called olympics.txt that is available to us in Runestone. Each line has information about one athlete's participation in the Olympics. It's actually a simulated file. Runestone can't access the real files on your computer for security and privacy reasons. So we simulate the presence of a few files in the Runestone environment so we can illustrate how file reading works. Python provides some functions for reading data from an existing file. There are two steps. First, you call the open function to open the file. So here we have an invocation of the open function, and we pass in two arguments. One is a string, it's the name of the file, olympics.txt, and the other says what to do with the file. In our case, R for reading. Later on, we'll see W for writing. The open function returns an object. It's a file object, and we are assigning it to this variable name called fileref. There's going to be an additional step that we're going to have to do to actually read the contents. So this step that we're showing so far just creates the file object. Then there are going to be some lines of code that we haven't written yet that will actually get the contents from the file and do something with it. And then there's a corresponding close operation that lets Python know that we're done working with this file object and it's okay to stop keeping track of it. So there's on line 3, fileref.close. Now if I run this, we're actually not going to see any output because all we've done is open the file and then close it. We haven't actually read the contents in, and we certainly haven't printed anything out, so you're not seeing anything in the output window. What if we did want to read the contents and print them out? There's a few different ways of working with file objects. The first method that we'll use is .read, which is going to bring in the entire contents of the file as a single string. Let me show you what that would look like. So we call the .read method on the file ref object. That returns a string, and I'm assigning that to the variable called contents. And then I could just print out, let's print out the first 100 characters of it. And now we'll see something in the output window. So we're seeing the first 100 characters from the file, which got us 3 lines and a little bit of the 4th line. Now you'll rarely use this method of reading the entire contents of the file all at once as a big string, partly because if you had a really big file, it would be a problem for your computer to handle all of that in memory all at once. The only times we're going to use this .read method is if you wanted to sort of grab the whole file and as a string and pass it to some other function that parses it. And even then, there'll usually be some other function available that will directly read from the file object a little bit at a time and parse its contents. So the second method that I'm going to show you is instead of reading it all at once, we have a .read lines method. Instead of getting everything as a single string, it returns a list of strings, one string for each line in the file. So let's print out, let's say, the first 4 lines of the file this way. And I forgot to rename the variable that I'm referring to. Let's call it lines, because I called it lines on line 2. And you can see now that we're printing out a list. So we've got the square brackets. And inside the list, there are 4 strings. Here's the first string. The second string begins here and is ending here, and so on. Each of the strings, notice, is ending with this special \n character. That's the new line character, because in the file we have a bunch of lines of text. So when we read these lines in, each of the strings has a \n at the end of it. Instead of just printing out all these lines, I could maybe get a slightly prettier printout if I iterate through them. So for line in lines, and maybe I'll just take the first 4 lines again, the first 5 lines, and I'm going to print the individual line. So now when I run it, it's going to iterate through these 4 lines, and each one of them is going to go on its own line. We're no longer going to get the square brackets to show up because we're not printing the whole list. We're iterating through the individual strings. We're also not going to get these quote marks because we're going to pass the strings, and when we print those out, we just show their contents in the output window. So let's see how that looks when we run it. And sure enough, we get each of the lines separately. Now you might notice something a little strange here, which is that we get these blank lines. The reason for that is that each of the strings, you'll remember, had that new line character at the end, which meant do a carriage return. And the print function always does a carriage return. And so we're getting 2 of those. One is starting us on a new line, and the other one is starting us on a new line again, so we get a blank line. What if we didn't want to have that extra blank line? Well, you've seen the .strip method before. I can strip the white space from the beginning and ends of each of these lines. So the .strip method gets rid of any white space at the beginning or the end. White space is the space character, a tab character, or a new line character. So if I call this, now I'm going to get the printout that doesn't have the blank lines. And sure enough, we've got the first 4 lines from the file. Now there's a shorter way to iterate over the lines if that's all we're going to do is iterate over all of them. So let me show you that because it's the more Pythonic way rather than reading the entire file into a list. We can just directly iterate over all of the lines by saying for line in file ref. So here it's a file object, it's not a list, but it knows how to be iterated over, and each time we get one more line. So this is going to do exactly the same thing that we had before, except now we're going to get all the lines in the file. So we can iterate over this file object directly. We can't do this thing of taking a slice of it like we did with lists. That gives us an error. So a file object supports iteration, but it does not support taking slices. So if we wanted to just do something with the first 4 lines, we'd have to use the .read lines rather than just iterating over the file object. But if we're prepared to process all the lines, which is the normal thing that you're going to do with a file, this is the standard Pythonic idiom. Now, when should you actually call .read lines or .read? Well, one reason to call .read lines is if you wanted to take slices. Another reason might be that you wanted to just get a count of how many lines are in the file. So if I get all of the lines and put them in a variable, I could now print out the length of lines. And that would tell me how many lines were in the file. I'm going to comment out the other 2. Turns out there's 60 lines in the file. If I wanted to find out how many characters are in the file, I could read the entire file as one character string, and then I could ask for its length. So except in those special cases, the more common thing that you're going to want to do is to just iterate over the file object itself. So we won't use .read or .read lines. Instead, we'll just iterate over the file object itself. This is the most common way that you'll be working with files. So that's Python code for reading from a file. We'll see you next time. So far, we've pretended that all files live in a single folder or directory, and it's the directory that your Python program is connected to. So your Python program doesn't need to specify a location for the file when opening it. With our simulated files in the Runestone environment, that worked fine. But if you're ever running Python on a local machine, it probably won't be enough for you. So let's see how you can have files organized into folders and directories and still find them in your Python program. So most people do organize their files into folders or directories because otherwise you just have hundreds of files in one directory and you can't find them. So for example, here's a diagram showing a hierarchy of directories and files. There's a top-level directory called My Files, and inside that directory we have 2 other subdirectories, Other Files and All Projects. All Projects itself has 2 more subdirectories called My Data and My Project. Inside of My Data, we've got a couple of files. One's called data2.txt. In My Project, we've got data1.txt and my Python program.py. By convention, we put Python programs into files whose name ends in .py. So a Python program, when we run it, is automatically connected to the directory where it's invoked from. We aren't invoking Python directly in the Runestone book, so we can't really see how that works. But I can give you a way to think about it, to use if and when you do install Python on your own computer to run it locally. In the open function, you can pass just a file name as we've been doing. like that. Open data1.txt for reading. But we also can specify a complete path that says where to find the file as well as the file's name. So normally we would use a relative path, which specifies how to get to another directory from the directory that you're currently connected to. So suppose that we're running this mypythonprogram.py, and we're running it from the directory myproject, and we want to open data2.txt. We can't just say open of data2. We have to tell it how to find it. So this is not going to work. We have to instead say, from the current directory, which is my project, you got to go up a level to get to all projects. And the way to say that you go up a level is to say dot dot. Dot dot says go to the containing or the parent directory. Within all projects, we have to go down, descend into the subfolder my data. We got to go down there. And now we've given the directions. Go up to the parent. Within that, go down to my data. And it looks like I forgot to capitalize the D. So let me fix that. And then now we're in the right directory, and now we can say data2.txt. Everything else is just the same. So that's called a relative path. This part is called the path. And then we have the file name. There's also a way to specify an absolute path that is absolute, meaning here's how to find this file on the computer rather than relative to the current directory that you're currently connected to. When you do that, you'll have a path that begins with slash. So it would be something like /user /presnick /myfiles. And you'd have to give the whole path all projects. After all projects, you would go to my data, and finally the file name. I don't recommend using these, what are called absolute paths, because it makes your code and data not portable. If I use the relative path and I take this entire set of folders and I just copy it to someplace else on a different computer, maybe somebody else's computer, not /user /presnick, then I can still find it. So generally, people prefer to use these relative paths because it makes their code and data more portable. You can transfer it to other computers. Now, if you've only been running Python in the Runestone textbook, you haven't had an occasion yet to use these file paths when opening files. And don't worry about it. Just make a mental note to come back to this video or the corresponding page in the book when you are executing in an environment with files grouped into directories. See you next time. Welcome back. Writing to a file is pretty similar to reading from a file. You still have to open a file object based on a name for the file, but instead of reading from the file object, you'll write to it. Let's see an example. Here we're printing out the squares of all the numbers from 0 up to but not including 13. So if I run it, we'll see we get 0 times 0, and 1 times 1 is 1, and then 4, 3 times 3 is 9, and so on. Now suppose instead of writing those to the output window, we wanted to write them to a file where they would be permanently stored. Well, let's start coding that up. Our normal little template for reading or writing from a file is that we have some file object equals open of some file name. I'll call it squares.txt. And now we have to say writing instead of reading. And whenever I open a file object like that, I tend to forget that I need to close it, so I'll just put the close in right away. Now if I run this, nothing different happens because I'm still printing to the output window. So instead of printing to the output window, I want to write to a file. So I'm going to say file obj.write instead of having a print statement. And I'm going to have to turn that number 014 or whatever into a string in order to be able to write it. The print function is pretty forgiving. We could give it a number or a string and it would figure it out. But here we have to actually give it a string. So if I do this, I will now have at the end in my file object all those numbers 0, 1, 4, 9, and so on. Now we have a little simulator for written files just as we have a simulator for reading from files. In Runestone, as you recall, we can't read or write files from the local file system for security reasons. So we have built in this ability to read a few files that are built into each page, and we can write files which will be available just until the page gets reloaded. So we have this file called squares.txt, and here's the output. Now that output may be a little different from what you were expecting because we have 0, 1, 4, 9, and so on. It's not nice like it was in the output window. We don't have 0, 1, 4, each on its own line. The reason for that difference is that when you call print and you give it a string like 4, you'll automatically get 4 and a new line in the output window. When we call .write, we just get the contents. So we just get the 4, but we don't get a new line character. You have to decide for yourself when you want a new line. So what I'm going to do is after I've written each square, I'm also going to explicitly write a new line, the \n character. Now if I save and run it, we'll see something that looks a little nicer in the data file. Now we've got all the values, each one on its own line. Of course, we could combine these onto a single line. We could have the string of square plus \n all on one line. That would work just as well. Sometimes, especially for students who are just learning, I like to make the new line character be its own line because it's a real reminder that with .write, you have to create that new line character explicitly, unlike with the print function where it does it for you. So that works just the same. Now, when we have a file, for the duration of this page being displayed, that file is available. So I could read it. I can read that file. It's called squares.txt, so new file object equals open of squares.txt. And this time I'm opening it for reading. And let's just print out, let's say, the first 10 characters. The .read gets me all the characters. If I just want the first 10 characters, I'll do that. And now we'll see something in the output window. Let me clear all of my markings. And there you see we've got the first 10 characters showing up in the output window. The first character is the 0, and then there's a second character for the new line, so that's 2 characters, 3, 4, 5, 6, 7, 8, 9, and 10. If I had asked for just the first 9 characters, I would have up to the 1 without the 6. And sure enough, there it is. Now, by the way, this file really is there, even if I don't recreate it each time with the code. I could now just read it if I wanted to. So let me get the first 14 characters, let's say, just so you'll see that we get something different. And sure enough, we get the 25 in addition. Now, as I said, we've simulated the creation of this file. It's there until we reload the page. Let me just demonstrate that for you. If I reload the page but try to keep this code, we're going to have a problem. It won't be able to find the file. So if I try to run this same code again, it says that there is no such file, a directory squares.txt. So it can't open it because it hasn't been created. That's how we write to files. It's structurally similar to reading. We open the file, just as we do for reading, but when we're writing, we do it with a quote W instead of quote R. We call .write as needed, but if we want a new line, we have to explicitly write the \n character. And then we have to close the file. It's especially important for writing because otherwise the contents might not be fully written and you might lose some of them. See you next time. Welcome back. We're going to see a little shorthand that makes it even easier to work with files and avoids the need to remember to close them. Python has an advanced feature called context managers. We don't need to worry about it in all of its generality, but it makes possible this nice recipe for working with files. It's easiest to understand it by example. You start with a special word with, and then there's another special word as. In between, you have the open statement. So we say open and the file name and whether you want to read or write it. After the word as, you have a variable name. So this is actually equivalent to saying md equals open of mydata.txt for reading. It's equivalent to that in the code block that's indented under the word with, we can refer to MD, and MD will be bound to our file object. But we get a behind-the-scenes action that happens at the end of the code block. It's as if we have an md.close. That gets executed behind the scenes. We don't actually have to specify it. It just gets done for us after everything else gets executed in that code block. If I run this, I just get the printout of the first line and the second line, as you might expect. Since we've iterated through the lines in the file object, printing each one, we get the printout of those 2 lines that were in the file. They're showing up in the output window. Let's get rid of our markings here and just generalize this a little bit. Suppose we didn't want to just open mydata.txt, but we wanted this to work with any file name. So let's say fname equals mydata.txt. We would open the file name here, and then we would do stuff with the file object. So we would have md.read or md.readlines, or we might have for line in md do something with each line. So now we have sort of a general recipe for reading data from a file. We start with this with statement, where we open a file object and we assign it to the variable name md. And then we use one of our three methods of working with the file. We either read all of its data in as a single character string with .read, or we read all of the lines as a list of character strings with .readlines, or we just iterate through those character strings directly using iteration over the file object on line 5. This same recipe will work just as well for writing files. So if I change that R to a W, I can do the same things that we would do for writing to a file. So for example, I might say for a number in range of 10, md.write of str of num, and md.write a new line character. And again, the close happens automatically for us. So when I run this, so unfortunately, I'm not seeing the file contents, and that reminds me of one little gotcha that you might want to remember. If you're trying to write a file, you can't write to a file that's the same name as one of the built-in files in the page. We have a little protective measure that keeps you from overwriting it. So if I just change the name of the file, now I get as my output what I was expecting. You can survive a long time as a Python programmer not using the with construct. But experienced programmers will use it. You'll see it on Stack Overflow and other help sites. So it's a good idea to be able to read it. And feel free to use it if you like. See you next time. We're chugging along here. You've learned the basics of reading and writing files now. There are two things that trip people up, so just keep these in mind. First, you have to pass a string, the file's name, as the first parameter when you call the open function. If you have a variable name whose value is the file name, don't put it in quotes. If you have a literal file name, do put it in quotes. Second, you have to keep track of the distinction between the file name, a string, the file object, which is the thing returned by the open function, and the file's contents, which you get by doing operations on the file object. I'm glad you made it this far. It's joke time. Reading. I had plans to read a book about sinkholes, but they fell through. Writing. There was once a young man who professed his desire to become a great writer. When asked to define great, he said, "I want to write stuff that the whole world will read, stuff that they'll react to on a truly emotional level, stuff that will make them scream, cry, howl in pain and anger." He now writes the error messages for the Python interpreter. See you next time. Welcome back. This lesson introduces the CSV format. CSV is an acronym. It stands for comma separated values, CSV. A file in CSV format is just a text file that follows certain conventions. The CSV format says that values are going to be separated by commas, and it says that every line of the file will have the same structure. So for example, we've got 2 commas on every line. 1, 2, 1, 2. And so we've got room for 3 things on each line: before the first comma, between the first and second, and after the second one. Usually you'll have the first line be special to give column names, and then afterwards all the rest of the lines are similar to each other. They each have values. The first value on line 2 is a name, the second value, 98, is a score, A+ is a grade. The reason this format is nice is that by having this standard format, you can have it read into lots of different programs. So I've chosen to name this file grades.csv, and it's saved on this computer. It's saved in this folder. On a Mac, when you have a file name that ends in .csv, unless you've configured your Mac some other way, when you try to open it, it defaults to thinking that you want to try to open it into an Excel spreadsheet. And so here, it's taken that, and instead of showing it to me as a text file, it's chopped it up and actually put the first values into column A, and the second values into column B, third values into column C. The same CSV format can be read not just by Excel, but by all kinds of statistics programs, Stata, R, SPSS, and so on. And you can also open it in Google Sheets. So here's my Google Drive folder where I have some of my notes for these recordings, and I've put that same grades.csv file here. When I double click on it, it gives me a little preview of what it would look like, and it gives me an option to open it with Google Sheets, which is just another spreadsheet program. And it's doing its little conversion. And now we see it again in columns. So the CSV format is kind of an interchange format. It's just a text file, but if you follow the conventions and have the same number of commas on each line, then it's going to be possible for a file to be read by any of these programs. At the end of this lesson, you'll be able to read a text file whose contents are in CSV format and parse the lines by using the .split method. And you'll be able to write a text file whose contents are in CSV format using either the .format method with a string template or the .join method. See you at the end of the lesson when I'll explain the difference between a cat and a comma. Welcome back. Since CSV is just a special format, you can read it like any other file. In fact, we've been reading a file that was in CSV format already, the Olympics file. It didn't follow the conventions of using .csv as the ending for the file name, but the actual contents were in CSV format. The advantage when we know that something's in CSV format is that it's easy to parse it. We can just chop up each line into its individual components by looking for where the commas are. For example, take a look at this code. On lines 1 through 4, I'm just reminding you of what the contents of this file are. So you can see the first line is a header, and then I'm printing out more lines up to line 6. Each line has somebody's name, and the other values, they're separated by commas. I want to show you how easy it is to process this contents, because we can just use the .split method looking for commas. So on line 6 of our code, we're looking just at the header line. That's this one. And we're saying, well, first of all, get rid of the new line character at the end of that line. And then split. And split wherever you see a comma. So where there's a comma, we're going to chop up the text, and we're going to get, well, actually we can see the output here because on line 8 we're printing it out. So we have name is the first value. It's the characters that occur before the first comma. And our next value is the string sex, and then we have the string age. All of these are coming from this one line of text, but we've chopped it up to make a list. And that's what the .split command does for us. We're doing something pretty similar with the rest of the lines. We're looping through all of them, and for each of them, we're chopping it up wherever you find a comma on the line. Now, once we take a line like A. Lamusi, M23, China, Judo, NA, and we split it up into a list, we can now use indexing. I can ask for the value that's in index 5, the sixth element from that line, and we can check, is its value NA? Well, sure enough, its value is NA, and we do one thing if it's NA, we do something else if it's not. In this case, if it's not NA, then we're going to print something out. So we're going to print out something only for the people who actually won a medal. We're going to skip the people who didn't win a medal. And you can see that output that comes down here. So only people who won a gold, a bronze, or a silver will show up in our output. And we're choosing here to not print the whole line. We're printing 3 elements from that line, the 3 curly braces, and we're printing out val square bracket 0. That's the name. It's the string that comes before the first comma, and we're getting the thing from the position 4 and from position 5. So that's the name and the event and the medal that they won. Now note that we have to split on commas. I think before, when we've seen the split command, we've tended to just split without specifying a value. And when you don't specify a value, it splits wherever it finds any white space, a space or a tab or a new line. If we do that, we're going to see that we get something different. We're not going to get this nice list here. We're going to get a different list. And sure enough, what we get is a list with only one element in it. It's one big string, all of its commas and everything. It hasn't split it up into 7 different elements or 6 different elements. It's just given us one big thing. And the reason is it was looking for white space, and in this whole string, there are no spaces, no tabs, no carriage returns, so we just get one item. If we had split on something else, let's say the letter E, it would split wherever there was an E, and we'll get some weird thing. Oops. I have to split on the character E, not the variable name E. And we're just waiting for it to finish, and sure enough, our first value is NAM, and then there was an E, and after that there's a comma and a capital S, and then there was another E, and so on. So split will split on whatever you tell it to split on. In our case, we want to split on commas, because the comma-separated value format says commas are the things that separate the values. By the way, there is another more advanced version of the CSV format that separates with commas but encloses all of the values in quotes. Let's see what that looks like. Here you can see in this file format, you can see that some events have commas in them while others don't. For example, we have speed skating, comma, 1,500 meters, whereas for tug of war or basketball, there's no comma in it. That's going to make it harder to parse, because when there's a comma, we don't know whether it's part of a value or separating values. If we were to just split on comma, like we did before, vals equals row dot split on comma, and then we said vals square bracket 5, like we did before, the fifth element, or the index 5, the sixth element of this row will be NA, but the fifth element of this row will be the 1,500 meters. So life gets more complicated when we want to parse this more advanced comma-separated values format that also has quotes around each of the values. It actually is still possible to unambiguously chop up the lines, but that's a harder programming challenge. I don't recommend trying it yourself. Instead, when you encounter something in this format, you would use Python's CSV module to parse the lines for you. We're not going to learn that module right now. I found that it's good for students to learn how to parse simple CSVs using the .split method at this point for understanding what's really going on. Later, you can learn to use the CSV module for harder formats. In summary, when we have a simple CSV format with commas separating and no quotes around all the values, parsing is easy. You just read in the file a line at a time, and you use the split method specifying comma as the thing to split on. That gives you a list of the individual values or the individual field names on the header line. We'll see you next time. Welcome back. To write a CSV file, you just need to write text strings that follow the comma-separated values format. Here we have the basic structure. You write a header line with field names separated by commas. You iterate through your list of objects, and for each one, you generate a line of output. What I've got here is just going to print the output to the output window. But it's in the CSV format, as you can see. We have one header row with the three headers: name, age, and sport. And then each line has the same structure. There's somebody's name and then a comma. There's an age and then another comma and then a sport. Now, if we want to change this, instead of printing to the output window, we want to write to a file, we'll do our usual transformation, where instead of print, we'll use .write. And we'll have to open the file and close it. So I've actually already got that code written out. I'm going to switch to it. So I've opened the file for writing. I've assigned the file object to this variable name outFile, and then I'm writing the header on lines 8 and 9, and with the row strings, instead of printing them out, I'm doing outFile.write, and because we're writing to a file, we have to explicitly put in the line breaks that we want. Instead of putting it in the output window, it's now in this data file, which is available until we reload the page. Again, the key to outputting CSV format is just generating a string that contains one line, where that line has commas that are separating either the field names or the values. There are two options that work well for generating a line with the commas separating the values, and a third one that I don't really recommend. As shown here, we're using the first method that I do like, actually the one I like the best, which is to use a format string. It's easy to see with this format string that we're going to have three values, because we have three pairs of curly braces, 1, 2, 3, and it's easy to see that we've got a comma separating each of them. And then the values are just going to get substituted in. The first element, John Alberg. The second element goes there, that's the 31, and cross-country skiing being the third element. A second possibility is to use the .join method. You may recall the .split method for chopping up a string into component parts. Its counterpart going the other way is the .join method. And I would write something like this: row string equals comma dot join of some values. And those values are going to be these same values that we used here. So I can use this instead. I'll comment out the old version. I always find this a little confusing, and I think many students do too. You might think that the natural thing is to call the join method and pass comma as a parameter, like we did with .split, passing comma as a parameter. But here, we're saying join is an operation that we do on the comma object, and we have to pass in as values the things that are going to be joined together. You just have to remember that that's sort of the opposite order of what you might expect. So it's comma.join. There's a couple other tricky things about the join operator, and I'll show them to you here. First, I'm going to get rid of our markings. When I run this, I'm going to get an error. There's actually two problems. The first problem is that join is expecting 2 arguments, and I've given it 4. So it really wants a list of things, not a bunch of different values. So I have to give it a list. I can put all of these values into a list. One other tricky part about it is that join wants to have a list of strings, or a sequence of strings. And Olympian square bracket 1 is the number 31. It isn't a string, it's an integer. So we get an error that it expected a string, but it actually got something different. Sequence item 1. That was Olympian square bracket 1. So if I turn it into a string, I'll finally have something that works. Now I get the same output that I was getting before. So this looks pretty complicated, and you're probably thinking, why would anyone ever want to do this? Well, if my values were all strings, then I might be tempted to do it. So now I don't need to say str of Olympian. I can just say Olympian square bracket 1 there, and it'll work. And the thing that really makes this attractive in this situation is that I can just refer to Olympian, which is already a sequence of strings. It's a tuple with 3 strings in it. I can call .join and pass that tuple of strings, and I still get this lovely compact code and the same output. So if you have a list of strings, then this .join method might be pretty attractive. If not, and you're going to have to do any kind of converting integers to strings or things like that, then I think you're going to want the version on line 13 that uses the format string. A third possibility is to just use string concatenation, but it gets really kind of hard to read it. And it also is still going to require us to convert the number to a string. So we're going to have something like this. And I think I'm pretty unlikely to get it right the first time. But I'll have row string equals Olympian square bracket 0 plus a comma plus Olympian square bracket 1 plus another comma plus Olympian square bracket 2. That might work. Let's see. Yeah, I got the right output again. So a little hard to read. My preference generally is to use the format string, like on line 13, unless I really have a sequence of strings, in which case I might be tempted to use the comma.join from line 12. Now suppose we had slightly different data, where one of the event names now has a comma in it. but not all of them do. Here you can see that cross-country skiing, we have the 15-kilometer is specified rather than the 100-kilometer, and some of the other events don't have commas in them. You may remember that one of the ways we can handle this kind of thing is with the advanced CSV format, where we put all of the values in quotes. So this is one of the nice things about Python having both single quotes or double quotes as a way of delimiting a string, is if we wanted to have double quotes as a character inside the string, we can use the single quotes as the delimiter, as I've done here on line 8. And with our format string, this is not too bad. We just have double quotes around each of the pairs of curly braces, and we're still going to substitute in where the curly braces are, so the value is going to be surrounded by the double quotes. This is a situation where I really appreciate the .format method. I wouldn't want to try this with .join, and I definitely wouldn't want to try it using concatenation with the plus sign. You'll see that our outputs have those quotes around all of the values. In particular, we've got quotes around the whole cross-country skiing, 15 kilometers. So there's a comma that's inside one of the values, inside the double quotes, and the other commas are separating the different values. To summarize, the overall structure for writing a CSV file is to write the header line. That's what we did on lines 8 and 9. Then iterate through all of your objects, and for each of them you're going to write one line into the CSV file. So I'm creating the row string, I'm writing it, and then I'm tacking on the \n to indicate the new line. We'll see you next time. Welcome back for a few tips on file names. Some older computer operating systems placed a lot of restrictions on file names. For example, early versions of Windows only allowed 8 characters before the period and 3 after the period. Modern computer operating systems have fewer restrictions on your file names. Still, it's a good idea for maximum portability of your files between computers to place a few restrictions on yourself. Here are our suggestions. First of all, don't use commas in a file name. So don't say Olympics, winter. Don't make that be a file name, even if your computer operating system allows it. Don't use more than one period, like .txt, .3, .csv. Don't do that. Don't use a / or a / in your file name. So Olympics/winter. That's usually the convention for making subdirectories. You don't want to have a slash in your file name or a / in your file name. Don't use spaces, even though most operating systems will permit that now. Olympic space winter, also not a good idea. Do follow some conventions for what happens after the period. .txt should be for plain text. .py, if you've got a file that's Python code. .csv, if you've got text that's in the comma-separated values format. So we've actually been bad here. We've got this file olympics.txt. It really should have been olympics.csv. Another file ending is .xls. That's for files that are in Microsoft Excel format. .doc or .docx for things that are in Microsoft Word format. The reason for following these conventions about what goes after the period is that computer operating systems will usually look at that extension, the .txt or the .csv or the .py. If you just double-click on the file, they'll decide which program to open. So if it's a .py file, they'll try to open it in a text editor, or they'll try to execute it as a Python program. If you have a .xls, it'll try to open it in Microsoft Excel, and so on. So that's all for now. Just a few words on naming conventions for your files. I'll see you next time. Welcome back. You should now be able to write a program that reads a text file in CSV format. You might get it as a dump from a spreadsheet or a stats program. And you should be able to write a text file whose contents are in CSV format. You can then import it into a spreadsheet or a stats program. CSV, comma-separated values. So, a joke about commas. What is the difference between a cat and a comma? Well, a cat has claws at the end of its paws, and a comma is a pause at the end of a clause. Which reminds me of another one in the same vein. What's the difference between a prince, a bald-headed man, a monkey, and an orphan? Right? What's the difference between a prince, a bald-headed man, a monkey, and an orphan? Well, the first is an heir apparent. The second has no apparent hair. The third has a hairy parent. And the last has nary apparent. See you next time.
Welcome back. In this lesson, we're going to learn about a new Python type called dictionaries. Dictionaries, like strings, lists, and tuples, are a collection of items. But unlike strings, lists, or tuples, they're an unordered collection of items, meaning that they don't have a first, second, or third item. They're kind of a bag of key-value pairs. In order to create a dictionary, we use curly braces. So this expression creates an empty dictionary. We assign this empty dictionary to the variable English to Spanish, or ing2sp. So that's what line 1 does. In order to assign one key value pair to this dictionary, then we say ing2sp and then specify a key that we want, and then we set it equal to whatever value we want. So if I go forward to line 2, you can see that first ing2sp starts out as an empty dictionary. Then when we run line 2, then we set one key value pair. So the key here is 1, and the value is uno. Unlike lists, strings, or tuples, dictionaries store key value pairs instead of just items. And what that means is that every dictionary has items that contain one key and one value. You can think of the key as the thing that you use to actually access the value. So for example, in a physical dictionary, the keys would be words and values would be their definitions. In the context of Python dictionaries, values can be any Python object, and keys can be almost any Python object, but we'll get to that more in a bit. So here we have the key 1 associated with the value uno. And that's because in this dictionary, ing2sp, we're going to associate English words with their Spanish equivalent. And we're going to use the English words as the keys and the Spanish equivalent as the value. So again, in our code, we first created an empty dictionary using curly braces, and then we assigned the value associated with the key 1 to be uno by saying ing2sp sub 1. And notice that this is a string because we have quotation marks around it. So the key string 1 is the value, the string uno. The next line associates the key 2 with the value dos. And you can see that our key value pair here gets added to the dictionary. Again, one thing that I mentioned in the introduction was that dictionaries are unordered, and that's actually kind of important. So there's no notion of what's the first item, the second item, the third item, and so on. Instead, just think of dictionaries as kind of a bag of key value pairs. You don't know what order you're going to get them in, but you know if you set 2 to dos and 1 to uno, that these key value pairs will be associated with each other, no matter what order they're in. On line 4 here, we set the value associated with the key 3 to be tres. So you can see, again, the order kind of changes around in our dictionary, but the important thing is that every key, so 3 is associated with trace, 2 is associated with dos, and 1 is associated with uno. Now, when we print out our dictionary, then we print out a list of key value pairs. So here you can tell that this is a dictionary because we have curly braces, and then every key value pair is separated by a comma. So we have 2 commas here, and our key value pairs are 3 is associated with trace, and we can tell because here we have a colon between the key and the value. 2 is associated with dos, and you can tell again because we have a colon between 2 and dos, and 1 is associated with uno. So here we always have the key first, and then we have colon, and then the value. Every one of these key value pairs is separated out by commas. And all of this is wrapped in curly braces to specify that it's a dictionary. You can also set these key value pairs in line. So whereas in this code, we set 1 to uno on line 2 and 2 to dos on line 3 and so on, we can also set them all on line 1. So if we instead declared our dictionary like this, so here, again, we can tell that this is a dictionary because we have curly braces, and then we have a list of key value pairs. Every one of these key value pairs is separated out by a comma. And then we have the key, so 3, associated with the value trace, and we specify that using a colon. So 1 colon uno, 2 colon dos. So now when we run line 1 and we look at our frames and objects, then we'll see that inc2sp is now associated with a dictionary that has 3 key value pairs. In order to look up the value associated with the particular key, we use square brackets. So here on line 1, we create a dictionary that has 3 key value pairs, just like before. And on line 3, we assign value to be inc2sp sub 2. So in order to get a particular value, we first say the name of the dictionary, inc2sp, then we use square brackets. And then inside of the square brackets, we put the name of the key that we want to get the value for. So here, the key is 2. And if we look at our dictionary, we can see the key 2 is associated with the value dos. So the value of this overall expression, inc2sp sub 2, is going to be the string dos. And what that means is that when we print out value on line 4, then we're going to print out dos. So you can see that running line 3 and 4, first on line 3 we assign value to be the string dos, which was the value of this expression. And then when we print out value in our program output, we get dos. So on line 5, we print out inc2sp sub 1, and the value of this expression is the value associated with the key 1 in our dictionary inc2sp. So if I look at the dictionary here, I can see that the value associated with the key 1 is uno. So the value of this expression is the string uno. And that's what gets printed when we print out inc2sp sub 1. That's all for now until next time. So let's go over some questions. So this is a true-false Boolean. So true-false, a dictionary is an unordered collection of key value pairs. That is absolutely true. That is what a dictionary is. And then we have a multiple choice. What's printed by the following statement? So here we declare a dictionary with 3 key value pairs, cat, dog, elephant. And then we print out my dictionary sub dog. So the value of this expression is whatever value is associated with the key dog in my dictionary. So in order to answer this question, we have to look at what's associated with this key dog. We find the key value pair for dog here, and we see that the value associated with the key dog is 6. And so we should expect 6 to be printed out. Then this question asks us to create a dictionary that keeps track of the USA's Olympic medal count. Each key of the dictionary should be the type of medal, so gold, silver, or bronze, and each key's value should be the number of that type of medal that the USA has won. So currently, the US has 33 gold, 17 silver, and 12 bronze. So again, the keys here should be gold, silver, and bronze, and the values associated with those keys should be the number of the medal that the US has won. And then they want us to create that dictionary and save it in the variable medals. So in the code, I'm going to say medals equals a dictionary, so I'll use curly braces. And first, I want to have the key gold associated with the value 33. If I just typed gold 33, which is common to do, then I would actually get an error. Because when I say gold, it's looking for a variable called gold. Instead, I want to make this key a string. So I want the string gold to be associated with the value integer 33. Same thing with silver. So silver is associated with the value 17, and bronze is associated with the value 12. And so here I just got each of these, so 12, 17, and 33, from the problem statement. So now when I run my code, then I should see that it passes. So this question is very similar. Here we're told you're keeping track of Olympic medals for Italy in the 2016 Rio Summer Olympics. At the moment, Italy has 7 gold, 8 silver, and 6 bronze medals. Create a dictionary called Olympics, where the keys are the type of medal, and the values are the number of that type of medal that Italy has won so far. So exact same idea. I'm going to say Olympics equals, and then we want to assign that to be a dictionary, so we use curly braces, and we have 3 key value pairs. So we have gold associated with the value 7. And then just for the sake of writing this out slightly differently, I'm going to set silver on the next line by saying Olympics sub silver equals 8. And so this is going to add a new key value pair associating silver with the value 8. And then I need to also say Olympics sub bronze equals 6. All right, so here I just did something slightly different. I could have added 3 value pairs right in here, like I did for the previous problem, but I could also just set the key value pairs using an assignment statement, like I did on lines 2 or on lines 3. And again, the keys are all strings, so here I'm using double quotes to create the string, here I'm using single quotes, but the effect is that we have 3 key value pairs. All the keys are strings, so gold, silver, and bronze. All the values are integers, 7, 8, and 6. That's all for now. Until next time. Welcome back. In this lesson, we're going to learn about some operations that we can use to modify dictionaries. So here on line 1, we create a dictionary. In this dictionary, we have 4 key value pairs. So the key pairs is associated with the integer 217, the string apples associated with 430, and so on. So overall, we have 4 key value pairs, and that's all created on line 1. Now on line 2, we do an operation called del. So del is short for delete, And delete deletes a key value pair from our dictionary. So when we say del, and then we say the name of the dictionary, and then in square brackets, the key whose key value pair we want to delete, that's going to get rid of that key value pair from our dictionary. So here we're saying del inventory sub pairs. So here our key value pairs is associated with the value 217, and line 3 says get rid of this key value pair. So when I actually run line 3, you'll notice the number of key value pairs will go from 4 to 3. If instead we created the same dictionary, so again, we're back to having 4 key value pairs, and now on line 3, rather than deleting the value associated with pairs, then we're going to set it to 0. So if you remember from when we first introduced dictionaries, we can set a key value pair by saying the name of the dictionary, sub, and then whatever key we want to set, equals whatever value we want it to be associated with. But the difference here is that by the time we run line 3, we'll already have a key value pair that associates the key pairs with a different value, 217. So when we say inventory sub pairs now equals 0, then that's going to update the value associated with the key pairs. So in other words, line 3 is going to say pairs is not 217 anymore. It's now associated with the value 0. So here, if we now run line 3, then you'll see the value of pairs is now 0. So let's reuse that dictionary in another example. So on line 1, we create the same dictionary that has 4 key value pairs that we saw from the previous examples. And now on line 2, we're setting that dictionary, so inventory sub bananas, to inventory sub bananas plus 200. Now, when we look at this expression is a little confusing because here we're repeating this expression inventory sub bananas. But remember that when we do an assignment, then what Python does is it first evaluates the value that we're going to be assigning to. So the first thing Python does on line 2 is it asks, what's the value of this expression, inventory sub bananas plus 200? After it computes this value, then it's going to assign whatever that value is to inventory sub bananas. So in other words, to figure out what this is going to do, we first have to ask, what's the value of this expression? So to figure out the value of this overall expression, let's break it down. So we add inventory sub bananas to 200. So we ask, what's the value of inventory sub bananas? To figure that out, we look at this dictionary and see that bananas is associated with 312. So this value is 312. And then we add 200 to that to get 512. And then Python takes this integer 512 and it makes it the new value associated with the key bananas. So this is going to now be 512 when we run line 2. So let's run line 2. And we see bananas is now 512. Now, if you remember the len function from strings or lists or tuples, remember that len gives you the number of items in a collection. So in the case of strings, len gives us the number of characters in that string. Len also works with dictionaries. So if we pass in the dictionary inventory, then when we call len on it, the value of this expression gives us the number of key value pairs in this dictionary. So the value of this expression is going to be 1, 2, 3, 4 because there are 4 key value pairs. So we'll see that num items in our frame right here is going to be assigned to the value, the integer 4. So let's run line 4, and we see that num items is now 4. So let's do some more questions. In this question, we ask, what is printed by the following statements? So here we create a dictionary with 3 key value pairs. And then we say my dictionary sub mouse equals my dictionary sub cat plus my dictionary sub dog. So the value of this expression, my dictionary subcat, is 12. The value of this expression, my dictionary subdog, is 6, meaning that the value of this overall expression, my dictionary subcat plus my dictionary subdog, is 12 plus 6, or 18. So then we assign the value 18 to be associated with the key mouse. And so by the time we print out my dictionary submouse, we're going to print out 18. So our answer is C. So this question asks us to update the value for Phelps in the dictionary swimmers to include his medals from the Rio Olympics by adding 5 to the current value. So Phelps will now have 28 total medals. And it asks us, do not rewrite the dictionary. So here on line 2, we assign swimmers to be a dictionary that has 1, 2, 3, 4, 5, 6 key value pairs, but we want to update the value associated with the key Phelps. And the way that we want to update it is by adding 5 to the current value. So the way that we're going to do that is we're going to say swimmers sub Phelps is now its previous value. So swimmers sub Phelps equals swimmers sub Phelps plus 5. So whatever it started out with, it's now going to be that plus 5. That's all for now. Until next time. Welcome back. So we've seen ways to get a value associated with a particular key in a dictionary. So for example, if we have this dictionary and we assign it to the variable inventory, and it has 4 key value pairs, if we wanted the value associated with the key oranges, then we would say something like print inventory sub oranges. But sometimes we don't want the value associated with just one key. We want the value associated with every key in that dictionary, or we want to iterate over every key value pair in that dictionary. In order to do that, dictionaries have a set of methods that we'll find useful. So the first method that we'll find useful is .keys. So if we want to loop over every key in our dictionary by using a for loop, so if I say for key in inventory dot keys, and then for now I'm just going to print out the key, so I'll say print key. When I run this code, then I'll see that I get all of the keys in my dictionary. Remember that dictionaries aren't ordered, so there are no guarantees what order I'll actually get these keys in. The only guarantee is that this for loop is going to run once for every key, regardless of order. So when I just print out the key, then I can see that there's apples, bananas, oranges, and pears are all the 4 keys in our dictionary. If I want to get the value associated with that key, I can say key has the value. And then to get the value associated with the key, I use inventory sub key. Now notice here that I'm not putting key in quotation marks. In other words, what I want is I want the value of the variable key. I don't want to look for the value associated with the key named key. So like if this dictionary had a key named key associated with the value 50, and I put key in quotation marks, then I would get 50. But here instead, I'm saying I want key, the variable's value, to be the key that I'm fetching. So now we'll see apples has the value 430, bananas has the value 312, oranges has the value 525, and pears has the value 217. So in order to actually get that list of keys into a list, one thing that I can do is I can just say keys equals a list of inventory dot keys. And if I now print out the value of keys, then I should get a list of keys in our dictionary inventory. But remember again that there's no guarantee about ordering here. So these keys could be in any order. The only guarantee is that I'm going to get a list that has all of the keys in some order. Now notice here that when I got the list of keys, I cast it to a list by calling the list function. And the reason that we'll do that, we're not going to get into too much yet, but on a high level, we always cast to a list because in Python 3, inventory.keys doesn't actually quite return a list directly. It returns something that we can actually iterate over, so we can put inventory.keys in our for loop, but in order to actually get a list of keys, we're always going to have to cast it to a list by calling the list function. If we wanted to iterate over inventory in a slightly less verbose way, we could just say for_k in inventory. So whereas here we're saying for_key in inventory.keys, here we're just saying for, I'll just rename this key to be consistent, for every key in inventory. When we say that, then Python automatically assumes that we want to iterate over the keys. So when I run this code, then I see got key and then every key in our dictionary. Again, no guarantees about order, just that we'll loop through every single key that we have. Dictionaries have two other methods that are somewhat similar to .keys. So .values, rather than getting a list of keys, gets a list of values. So 430, 312, 525, and 217. So .values would give us a list that has all of these integers, but again, there are no guarantees about ordering. So we know that it's going to be a list with these 4 items. We just don't know what order inventory.values is going to be in. Inventory.items instead gives us a list of key value pairs as tuples. So inventory.items is going to give us a list, and the first item might be apples and 430. Again, I say might be because we don't know what the ordering is, but the second item might be oranges associated with the value 525. And then we might have bananas, and so on. So .item gives us a list of tuples where every tuple is a key value pair. So on line 3, we print out the value of inventory.values, and on line 4, we print out the value of inventory.items. So let's see what these two lines output. And I'm going to, for now, comment out lines 6 and 7. So we can see that when we printed out inventory.values, then we got all of the values. And they aren't necessarily going to be in the order that we actually created the dictionary in, but in this case, they just happen to be in that order. When we called inventory.items, then you can see that we have a list of tuples of key value pairs. So here, this first tuple says that the value of the key apples is 430. The value of the key bananas is 312, and so on. We can also use the same in operator that we saw on lists and strings on dictionaries. So if we print out the value of this expression, apples in inventory, then the value of this expression is going to be a Boolean. The value of that Boolean is going to be true if this is a key in our dictionary. So if apples is a key in inventory, and false otherwise. Now, it's crucial here that I mention that it's true only if apples is a key in our dictionary. It can't be a value, it has to be a key. So when we print out the value of apples in inventory, then we can see here that we have a key value pair where the key is apples, so this should be true. If we print out the value of cherries in inventory, then if we look at our key value pairs, apples, bananas, oranges, pears, we don't see anything that has the key cherries, so this is going to be false. So if we comment out this code and just run lines 2 and 3, then we should see the value of apples in inventory is true, the value of cherries in inventory is false. Now, we can also write code that depends on the values of these Boolean expressions. So we can say if our dictionary has the key bananas by saying if bananas in inventory, again, this expression is a Boolean that's true if bananas is a key in our dictionary. In this case, bananas is a key. So if that key is in our dictionary, which in this case it is, then we print out the value of inventory sub bananas. Otherwise, if bananas is not a key, we say we have no bananas. So here we're going to print out 312, which is the value associated with bananas. If I modified this key to be something else, I'll literally call it something else, then we would see we have no bananas because bananas is no longer a key in our dictionary. Another method that we can use on dictionaries is .get. So .get works almost just like indexing. So we can say inventory.get apples, and the value of this expression is going to be the same as the value of inventory sub apples, which in this case is going to be 430. So if I just run line 3 and comment out lines 4 and 6 here, then I see that I get 430. Now, on line 4, we say print out inventory.getCherries. Now, notice here that cherries is not in our dictionary, so we don't have any key whose value is cherry. So when we run this code, then we get the value none. This is the difference between .get and actually indexing, because if we indexed here, so if we said print out inventory sub cherries, we would instead get a runtime error because cherries was not a key in our dictionary. If we instead call .get, then we get kind of a softer error. So instead of actually giving us a runtime error that stops our program, .get says the value is none. .get also takes an optional second argument, which is to say that if this key isn't there, then this is what the value of that expression should be. So here when we say inventory.getCherries and then we pass in a second argument of 0, then this is going to say if cherries is in our dictionary as a key, then get the value associated with it. If cherries is not a key in our dictionary, then just use this as the value. This isn't going to add a key value pair with cherries, it's instead just going to say the value of this overall expression should be 0. So when we run our code, we see that now when we call inventory.getCherries with the optional argument 0 here, we instead get 0 because cherries isn't a key in our dictionary. If we had 999, then we would get 999. And if we had a key cherries in our dictionary, let's say it's 5, then we would instead get 5. That's all for now. Until next time. So in this question, we asked what's printed by the following statements. So myDict is a dictionary with 4 key value pairs, and we print out myDict.getCat divided by myDict.getDog, Here we're using division without a remainder, which just gives us an integer. MyDict.getCat is 12, and MyDict.getDog is 6, and so the value of 12 over 6 is going to be 2, so A. In this question, we're asked what's printed by the following statement. So we create that same dictionary, and now we print out the value dog in MyDict. So that asks, is dog a key in my dictionary? And we can see that it is. It has the value 6, but all we care about is that it is a key. Here we create that same dictionary, and we print out the value 23 in MyDict. And here we have a key elephant that has the value 23, but remember that in only asks, is 23 a key in my dictionary? And in this case, it's not. Our only keys are cat, dog, elephant, and bear. It doesn't matter that it just so happens to be a value. The value here of this overall expression is going to be false. So here, we first assign total to be 0, and then we create the same dictionary that we had before, and we loop through all of the keys in our dictionary. So a key is going to be cat, dog, elephant, and bear, not necessarily in that order. And we say if the length of that key, so every one of these keys is a string, so if that string is longer than 3 characters, then add its value to total. So the first thing I would ask are, what are the keys that are longer than 3 characters? And that's just going to be elephant and bear. And so for cat and dog, this statement is not going to run because the key cat is not longer than 3 characters, and same thing for the key dog. So for elephant and bear, then we're going to say total equals total plus my dictionary plus that value. So we're going to first assign total to be 0 plus, let's suppose that elephant comes before bear. So 0 plus my dict sub elephant, so 0 plus 23. So total gets the value 23. And then by the time we get to the key bear, then we're going to say total equals its old value, so 23, plus the value associated with the key bear, which is 20. So 23 plus 20, which is going to leave total at 43. So the answer here is going to be B. That's all for now. Until next time. Welcome back. One more thing to note about dictionaries is aliasing. So on line 1, we create a dictionary that has 3 key value pairs. And on line 2, we assign a new variable called alias to be that dictionary. On line 4, we print out is alias opposites. And this is asking, are they pointing to the same object? So if we run CodeLens on lines 1 through 4, then we'll see again line 1 creates a dictionary, and line 2 assigns alias to point to the exact same object of that dictionary. Now this is important because here, if we say alias sub right equals left, reassigning right from its previous value, which was wrong, and then we print out opposites sub right, then we're actually going to print out left on line 7. So here we can see line 4 says true because alias is the same object as opposites, but now when we print out opposites sub right, we now get left. And that's despite the fact that we first assigned opposite sub right to be wrong. And in all of these lines, we never directly changed opposites sub right. But the culprit here is that on line 6, when we changed alias sub right to be left, then that also changed opposite sub right. Again, we can use CodeLens to see why that is. So on line 1, we create a dictionary, and then we assign alias to be that exact same dictionary, and we can see alias is opposites. And now when we assign alias sub right to now be left, then that modifies that dictionary so that right is now left, And that changed the value associated with the key right to be left for both opposites and alias. So let's go through a question related to this. So here on the first line, we create a dictionary with 4 key value pairs, and then we assign your dict to be my dictionary. So your dict is pointing to this same dictionary, and then we say your dict sub elephant equals 999. Now remember, your dict and my dict are the same object here, so when we assign it elephant to be 999, that erases the value 23 and replaces it with 999 for both of these dictionaries because they're pointing at the same object. So now when we print out my dictionary sub elephant, then we're going to get the value 999. That's all for now. Until next time. Welcome back. So we've already gone over the accumulation pattern, where you iterate over a sequence and update an accumulator variable as you iterate through every item in that sequence. In this lesson, we're going to go over the dictionary accumulation pattern, which is the same idea, except our accumulator variable is going to be a dictionary that has multiple key value pairs. So let's start out with the standard accumulation pattern example. So on line 1 here, we open a file named scarlet.txt, and we open it to read it. And then we say text is f.read. So in other words, txt is a variable which is a string, and it's the contents of the file scarlet.txt. So suppose scarlet.txt represents the text of the book The Scarlet Letter. So let's say that we want to keep track of how many t's are in scarlet.txt. The way that we would do that is with the accumulation pattern. So here, tcount is our accumulator variable. We initialize it to be 0 at first to say that we've seen 0 t's so far, and then we iterate through every character in our text file, and we say if that character is the letter t, then say tcount equals tcount plus 1. In other words, we just saw one more character t. So by the time we're on line 8 and we're done with our for loop, if we print out the value of tcount, then we should have the number of t's in scarlet.txt. So if I run my code, then I'll see that here there are 17,584 occurrences of the character t in scarlet.txt. So that's great, that's the standard accumulation pattern, but let's suppose that we wanted to count more letters than just the letter t. So suppose that we also wanted to keep track of how many s's are in scarlet.txt. Well, we could do that in almost the same way. So here we open up scarlet.txt again, and then we read it. Except now on lines 4 and 5, we create 2 different accumulator variables. We have tcount to keep track of the number of t's, and we initialize that to 0. And then we have scount to keep track of the number of s's. Like before, we still iterate over every character in txt, but now we say if that character is a t, then tcount is tcount plus 1. If the character is an s, then we instead update scount. So by the end of our for loop, tcount is going to be the number of t's, and scount is going to be the number of s's. So you could imagine doing this for any number of characters, but for every character that we would want to accumulate, we would have to create a new accumulator variable here. So we might have a count, then b count, then c count, and so on. And you can imagine that if we wanted to count every character in the alphabet, initializing 26 accumulator variables might be just a little bit lengthy code-wise. So one alternative way to do this, and it's going to seem a little bit weird at first, but I'm going to get to why we want to do this, is by instead using a dictionary. So like the code before, we open up the file scarlet.txt, and then we read it in. And now I'm going to have one accumulator variable, which is a dictionary. So I say x equals an empty dictionary. inside of that dictionary, we're going to have multiple key value pairs. So if we wanted to still only count t's and s's, then rather than saying t count equals 0, I'm going to say x sub t equals 0. And rather than saying s count equals 0, I'm going to say x sub s equals 0. Now, these are just different key value pairs in this same dictionary X. So now what we can do is we can loop through every character in our file once again. And again, we say if that character is a t, then our dictionary X sub t equals its previous value plus 1. If that character is an s, then X sub s gets incremented by 1 instead. And again, by the time our for loop is done, then we're going to have x sub t as the number of t's in our dictionary, and x sub s is going to be the number of s's in scarlet.txt. So when we run our code, then we can see the number of t's and the number of s's. So now I'm going to make one really small change to our code. So here on line 9, this statement is inside of if c equals the character t. So what we can do is we can replace x sub t here. So we can replace the hard-coded t with the variable c. We know that this is going to be the same because here we only run this code if c is the character t. So we can say x sub c equals x sub c plus 1. And here we can say x sub c equals x sub c plus 1 because this line is inside of this elif c equals the character s. So in other words, what we're going to just do in the next piece of code is we're going to replace the hard-coded s and hard-coded t with the value of the variable c. So if we do that, we get something that looks like this. So we say if the character c is t, then say x sub c equals its previous value plus 1. Now, because again, this is inside of an if statement, we know that c is going to be t here, but we'll get to why we actually want to make this change in a little bit. Same thing with this elif. So we know that c is going to be the character s here, but we just replaced the hard-coded s with the value of the variable c. If we run our code, we're going to get the exact same result as before. So now I want to go into why we actually wanted to replace that hard-coded t and hard-coded s with the value of the variable c. So let's suppose that rather than just counting the number of t's and the number of s's in scarlet.txt, we wanted to count the number of every single character, so the number of a's, b's, c's, s's and t's, spaces, exclamation points, and so on. So we could do that by replacing line 4 with a whole bunch of accumulator variables, so a count, b count, c count, exclamation point count, etc. But then our code would get really long and really repetitive because we would need to initialize a separate accumulator variable for every single character that might be in scarlet.txt. Instead, what we're going to do is the dictionary accumulation pattern. So we're going to have one accumulator variable, which is a dictionary. So on line 4, we say x equals an empty dictionary. And then, like before, we loop through every character in txt. And what we do is we have an if statement to say if the character c is not in our accumulator dictionary, so if c is not an x, so in other words, if we haven't encountered this new character c yet, then we initialize x sub c to be 0. What that means is that the first time we see the character a, then we're going to initialize x sub a to be 0. The first time we see the character t, then we initialize x sub t to be 0, and so on. Now here on line 11, still inside of this for loop, we say x sub c equals x sub c plus 1. In other words, we add 1 to its previous value for whatever this character c is. So in other words, if the character C is the letter A, then we say x sub A equals x sub A plus 1, and that says that we saw one more A. If the character is the letter T, then we say x sub T equals its previous value plus 1, and so on. So here on line 13, we just print out the number of characters T and the number of characters S on line 14. So what we should find is that we actually get the exact same value for T and S as before. So if I run my code, then we'll see that we get the correct number of T's and S's. But what's great here is that we have more than just T's and S's collected. We can print out the number of any character we want. So I can print out the number of A's just by saying the number of A's is x sub A, and the number of B's is x sub B. And you'll see that our dictionary is keeping track of every single letter that might occur in scarlet.txt. So to illustrate how this works, I'm going to go with just a slightly simpler example. So rather than assigning txt to be the value in scarlet.txt, I'm just going to say txt equals the string Michigan. And I'm going to leave the rest of the code the same, except I'm going to comment lines 12 through 15. Now I'm going to run my code in CodeLens. So you can see line 1 initializes txt to be Michigan. Line 3 initializes our accumulator variable x to start out as an empty dictionary. And then we're going to loop through every character inside of our string Michigan. So C is first assigned to the character M because that's the first character. And we say, is C in our dictionary already? In our case, it's not. So we assign x sub C or x sub M to be 0. And now on line 10, we immediately increment the value associated with x sub M. So we say we've seen one M so far. With the character I, then we see that I is not in our dictionary. So we initialize x sub I to be 0, and we set its value to its previous value plus 1. With C, it's not in our dictionary, so we initialize it to 0, and then increment it. With H, we set it to 0, and then increment it. So you can see that our dictionary keeps building up the number of times that we've seen every given letter. So at this point, we've seen M, I, C, H, and so far, none of these characters were in our dictionary, and so our dictionary was just adding a new key value pair for every letter that we saw. Now, the next character is going to be this letter I. So you can see C is the character I. Now, the key point here is that I is already in our dictionary. So here, this if is not going to execute because I is in our dictionary. And so rather than setting x sub I to be 0, we just increment it on line 10. So you'll see x sub I go from 1 to 2 to say that we've seen 2 i's so far. In the case of G, it's not in our dictionary, so we add a new key value pair and increment its value, and so on. So by the time our for loop is done, then we end up with the dictionary where every key is a character in our text txt, and every value is the number of times that we've actually seen that letter. So we'll see dictionary accumulation a lot, and really I find that it just takes a lot of practice to get used to. It's a little bit counterintuitive at first, but we're going to go through more examples with dictionary accumulation, and I think it's going to make more and more sense with more practice. That's all for now. Until next time. Welcome back. So let's go over some questions that use dictionary accumulation. In this question, we're provided a string sentence, and the question asks us to split the string into a list of words, and then to create a dictionary that contains each word and the number of times it occurs, and that dictionary should be named word counts. So the first thing that I'm going to do is I'm going to split our sentence into words. We can do that by calling the split method on string. I'll say words equals sentence dot split. And so words is going to be a list of strings. The first item is going to be the second item is going to be dog, the third item is going to be chased, and so on. So then we want to use dictionary accumulation. And in this question, we're told to use the dictionary word counts. So I'm going to name my accumulator variable word counts. And I'm going to initialize it as an empty dictionary. Then we need to loop through all of the words. So I'll say for every word in words. And we want to say if that word isn't in our dictionary so far. So if word is not in word counts, and if it's not there, we initialize its value to 0. So word counts subword equals 0. And then still inside of our for loop, but outside of the if statement, we're going to increment the value of word counts subword. So word counts subword equals word counts subword plus 1. So let's run our code, and we can see that it produces the correct value. If I actually print out the value of word counts, so if I say print word counts, then we can see that the word the with a capital T appeared 1 time, the word the with a lowercase t appeared 3 times, into appeared once, rabbit appeared twice, and so on. In this question, we're asked to create a dictionary called char_d from the string stri, so that the key is a character and its value is how many times that character occurred. So this is, again, a straightforward application of the dictionary accumulation pattern. So I'm going to name my dictionary accumulator char_d. Then I loop through every character in stri, so I'll say for c in stri. And if I haven't seen that character before, so if c is not in char_d, then char_d sub c equals 0. And then inside of the for, but outside of the if, I say char_d sub c equals its previous value plus 1. So when I run my code, then I can see that it worked correctly, but let me run this code in CodeLens just to see again what's going on here. So on line 1, we initialize stri to be the string, what can I do? On line 3, we initialize our accumulator variable, our accumulator dictionary, to be an empty dictionary. Then we loop through every character in stri. So we first say c is the character w, or the first character, and then we say if c is not in char_d, which it is not, so we assign char_d sub c or char_d sub w to be 0, and then we increment it. Same thing with the letter h. So h isn't in our dictionary, so we're going to add it and initialize its value to 1. Same thing with a. The character a was not in our dictionary, so we initialize it to 1. Same thing with t. Same thing with the character space and c. So at this point, we're at this a, and we're going to see that a is in our dictionary. We're going to skip this if, and we're going to say char_d sub a equals its previous value plus 1. So we'll see this update to be 2. And then we keep adding characters as we go on. The second time we get to a space, so at this point we're at this space, then we'll see this value increment by 1, and so on. That's all for now. Until next time. Welcome back. So we've learned how to do the dictionary accumulation pattern, but now we want to learn some things that we might want to do with our accumulated dictionary. So rarely do we just want to do something like accumulate the number of every character in a dictionary, we typically want to actually do something with that data. So here we have the same code as before. So we open up the file scarlet.txt, load its contents into the variable txt, and initialize our accumulator variable letter counts to be an empty dictionary. And then through this for loop, we associate every key in letter counts, which is going to be a character, with the number of times that character appears in scarlet.txt. So in other words, by the time we get to line 12, then letter counts is going to be a dictionary where every key is going to be a character, such as T, and every value is going to be the number of times that character appeared. So in the case of T, it's 17,584. So in our code before, we just printed out the number of T's by printing out there are, and then something like letter count sub T, T's in scarlet.txt. We can do the same thing with other characters, of course. So we can say that there are this many A's and B's and so on. But suppose that we wanted to print out the number of every single character in letter counts. Well, we could do that by using a for loop. So we could say for every character, so for every, I'll just call my iterator variable y in letter counts. And then inside of our for loop, we can just say there are, and then letter counts sub y. And we can say that there are that many of the character y. So what this code is going to do is it's going to loop through all of the keys in letter counts, and for every key, y is going to be the value of that key, and then we're going to get the number of times that character y appears by printing out letter count sub y, and then we say there are that many, and then whatever that character y is. So when we run our code, we can see that there are this many T's, this many S's, this many spaces, this many capital T's, and so on. And you can see that there are quite a few characters in scarlet.txt. So let's suppose that we had called our dictionary X instead of letter counts. In this question, we're asked, which of the following will print out true if there are more occurrences of the character E than the character T in the text to study in Scarlet, and false if T occurred more frequently? So this is assuming that our previous code has run, except our dictionary is called X instead of letter counts. So we want to write an expression that's going to be true if there are more E's than T's. So the way that we do that, we get the number of the character E by saying X sub E. This is going to get the value associated with the character E in the dictionary X. And then we get the number of T's by saying X sub T. If we want to know if there are more E's than T's, then we can write the expression X sub E is greater than X sub T. So in other words, the answer here is going to be B. So if you've ever played the game Scrabble, then you know that different letters in Scrabble have different scores. So letters that are more rare have a higher score than letters that are more common. So let's suppose that we want to open up scarlet2.txt and we want to figure out what's the quote-unquote Scrabble score for this. So in other words, for every character, suppose that we want to know not just how many times that character appeared, but what the Scrabble score for that character would be. So from lines 1 through 11, we have the dictionary accumulation pattern, and it accumulates the frequency of every character in scarlet2.txt into this dictionary X. And then on line 13, we have a different dictionary which represents the Scrabble letter value of every character. So An A, which is a really common letter, only has a score of 1, whereas a Z, which is a lot less common, has a Scrabble value of 10. So if we wanted to get the Scrabble score in scarlet2.txt, then what we could do is we could loop through every character inside of the dictionary letter values. So I'll say for every character, I'll call it Y in X. And then because not every character has a Scrabble score, so for instance, numbers or exclamation points don't have Scrabble scores, but they're in our dictionary, we want to first check to see, is that character Y in letter values? So I'll say if Y is in letter values. And we want to keep track of what's our letter value so far. So the way that we do that is with the standard accumulation pattern. So I'm going to initialize an accumulator variable. I'll call it Scrabble score. We initialize it to 0. And then we say, if this character Y has a letter value, then Scrabble score equals its previous score. So Scrabble score equals Scrabble score plus, and then we want to add the score for that letter. So in other words, A has value 1, B has value 3, C has value 3, and so on. So we get that score by saying letter values sub Y. Again, Y is going to be A, B, C, D, E, F, G, and so on. And then we want to multiply that by the number of times that that character appears. So I'll say letter values sub Y times X sub Y. X is, again, our dictionary accumulator variable from the previous problem. So in other words, we're saying the score is the previous score plus the value of that letter times the number of times that that letter appeared. So this is using the standard accumulation pattern. Here, our accumulator variable is Scrabble score, and we update it by saying Scrabble score equals Scrabble score plus letter value sub Y times X sub Y. So if I print out the Scrabble score at the end of this for loop, then I should expect it to be the actual Scrabble score of scarlet2.txt. So you can see that this has a pretty high Scrabble score overall. Let's do some more questions that involve dictionary accumulation and doing something after we accumulate the results from the dictionary. So in this question, we're told the dictionary travel contains the number of countries within each continent that Jackie has traveled to. And we're asked to find the total number of countries that Jackie has been to. In other words, our result is going to be 2 plus 8 plus 3 plus 4 and so on. And we're asked to save that into the variable named total. And so in this question, we're given a dictionary, and it doesn't matter how we arrived at this dictionary. So we might have 20 lines before this that compute this dictionary's value, or in this case, we're just given the dictionary as a literal object. But regardless of how we get that dictionary, what we want to do is we want to accumulate the sum of every value associated with every key in that dictionary. So we can do that with the standard accumulation pattern. So I'm going to first initialize an accumulator variable total to be 0. So this is initializing our accumulator variable. Then we want to loop through every single continent. So I'll say for continent in travel. So continent is going to be North America, Europe, South America, Asia, Africa, etc. So for every continent in travel, we get the number of countries within that continent that Jackie has been to by saying travel subcontinent. And we want to say total equals total plus travel subcontinent. So this is us updating our accumulator variable. So again, what we're doing is we're looping through every key in our dictionary, and we're getting the value associated with that key, so 2, 8, 3, and so on, and adding that value to our previous total. And by the time we're done with our for loop, we should have the total number of countries that Jackie has been to. In this question, we're told that schedule is a dictionary where a class name is the key and its value is how many credits it's worth. We're asked to go through and accumulate the total number of credits that have been earned so far and assign that to the variable total credits. So this is the same idea with just a slightly different dictionary. So our accumulator variable is going to be named total credits. We're going to initialize it to 0. Then we want to loop through every course in our schedule. So I'll say for course in schedule. So again here, course is going to be UArts 150, Spanish 103, English 125, and so on. We get the number of credits for that course by saying schedule subcourse. And we add that to the total number of credits by saying total credits equals total credits plus schedule subcourse. That's all for now. Until next time. Welcome back. In this question, we're asked to create a dictionary called D that keeps track of all of the characters in the string placement and notes how many times each character was seen. So in order to do this, we're going to kind of use the standard dictionary accumulation pattern. But this isn't all that this question asks us to do. It says then find the key with the lowest value in the dictionary and assign that key to be min value. And in order to do this part of the question, then we're going to use the standard accumulation pattern. More specifically, actually, we're going to use min or max value accumulation. So let's do this first part, which involves dictionary accumulation, first. So I'm going to create a dictionary, D, initialize it to an empty dictionary, and I'll loop through every character in placement. So I'll say for every character C in placement. If that character is not in our dictionary, so if C is not in D, then initialize D sub C to be 0. And then regardless, we're going to say D sub C equals its previous value plus 1. And now, by the time we get to line 9 here, we've accomplished this first part of the question. So we have a dictionary D where every character is associated with the number of times that that character appears in placement. Now let's do the second part, where we want to find the key with the lowest value in this dictionary and assign that key to be min value. So the first thing that I'm going to do is I'm actually just going to get a list of keys. So I'm going to say keys equals list of d.keys. So keys is going to be a list, and every item in that list is going to be a character. So we might have one item as the character A, one item as the character E, one item as the character C, one might be a space, and so on. So keys is a list of the characters in placement, or a list of all of the keys in our dictionary D. And now we want to get the key that has the lowest value in our dictionary D. So we're going to use max value accumulation. In this case, we actually are searching for the minimum value, but it's the same concept. So I'm going to initialize min value to be keys sub 0. I'm just going to do this arbitrarily to give us a starting point. So in other words, min value is going to start out as the first key in our list of keys. So it might start out as something like the character A. And then we're going to search for any key that has a lower value associated with it. So I'll say for every key in keys, and I'll ask, is the value associated with this key? So if D sub key is less than the value associated with min value, so if D sub key is less than D sub min value, then we say our new lowest key is this new key. So I'll say min value equals key. So again, we kind of have two parts in this question. The code from line 3 through 8 addresses the first part, where we create a dictionary with character frequencies, and then lines 10 through 15 address the second part of finding the key with the lowest value. We use information from this first part, in other words, we use this dictionary D in the second part, but we kind of apply the accumulation pattern 2 different times to solve this problem. So when I save and run my code, I can see that I get the correct values. So in this question, we're asked to create a dictionary called letD that keeps track of all of the characters in the string product and notes how many times each character was seen. And then we find the key with the highest value in that dictionary and assign that to be max value. So again, here we have kind of 2 different parts. The first part uses dictionary accumulation. The second part uses max value accumulation. So to do the first part, we're going to create a dictionary let underscore D, initialize it to an empty dictionary. Then we're going to loop through every character in product, and we're going to say if that character is not in let D, then let D sub C is initialized to 0. Then we say let D sub C equals its previous value plus 1. So if I print out the value of let D at this point, then I should get a dictionary where keys are associated with the number of times that character appears. Now we want to find the key with the highest value in this dictionary. So in this case, it's going to be n. So I'm going to get a list of keys. I'll say keys equals list of let D dot keys. And for every key in keys, actually first I'm going to say max value equals the first key. And for every key in keys, if the value associated with that key, so if let D sub key is greater than let D sub max value, then I've seen a new largest value, so I'll say max value equals key. Now, when I run this code, then I should see that I pass every test, and max value ends up being n, which was the correct answer. That's all for now. Until next time.
Welcome back. Take a look in your calendar and mark this date. Today is the day you are crossing over the line from someone who can just write code that does something to being a real programmer. Someone who can abstract from a bit of code that works on one piece of data to writing a function that will operate on any similar piece of data. Today is your day, and I hope you'll celebrate in some way. Have a special treat, brag to your friends, or at least make a celebratory post in the forums. At the end of this lesson, you will be able to define functions with appropriate names for formal parameters, identify formal parameters and parameter values in a code sample, and you'll be able to predict the return value of a function given sample parameter values. See you next time. Welcome back. The basic syntax for defining a function is the word def. DEF is short for define. Then you get any Python variable name. And then you have an open and close parenthesis. Inside the parentheses, we're going to see later that you could have more variable names, but we don't have any for this function. And then we've got a colon. Below that, you've got an indented block of code. You've already seen indented blocks of code with the while loop, the for loop, or if statements. It works the same way for function definitions. All the lines that are indented by that same number of spaces, they're all part of the function definition for the hello function. And when we get another line of code down here on line 5 that's outdented at the same level as def, that's going to be the end of the function definition. We have an optional comment on the first line of the function. If it's included, it's called a doc string. And there are some tools in Python for automatically generating documentation of a program. They'll show the doc strings that are associated with functions. It's often a multi-line string, and that's why we use this triple quotes. We could have some more doc string here. The triple quotes lets you have a string that goes on to multiple lines. Now, when we execute just the code that we have here, nothing is going to print out. Even though there are 2 print statements on lines 4 and 5, they won't actually be executed. All that happens from lines 1 through 5 is that the function object gets created. That function doesn't get executed. Lines 4 and 5 here are only going to execute if we invoke the function. So I'm going to have some code that's outdented at the same level as the def, and I'm going to invoke the function hello. Now, when we execute it, lines 4 and 5 will run. And it says, hello, glad to meet you. Suppose I print something that says, we are here, and then another invocation of hello. See if you can predict what we're going to get in the output window. So what we get is the first 2 lines come from our first invocation of hello, and then we get the we are here, and then we get 2 more lines that come from the second invocation of hello. Let's see that in CodeLens. So you can see that executing lines 1 through 5 just creates a variable called hello, whose value is a function object. It doesn't execute that function object. When I invoke the function on line 7, it passes control to the function. So we then actually execute the contents that are inside of it. So we execute line 4, which prints out hello. We execute line 5. And now we're done. So we're going to resume back here after the execution of hello. So we get to line 8, and we print we're here. And then we have another invocation. So that passes control to the function. It does its stuff, and then it passes control back after line 9, and we're at the end of the function execution. So that's the basics of function definitions. The syntax, we start with the word def, and then we have a function name, and then parentheses, and then a colon. We've got an indented block of code for the contents of the function. Executing the def statement, that just creates the function. It doesn't execute it. We need other code afterwards, like we have on line 7. When we do a function invocation, it passes control to the code for the function. So those lines of code inside the function get executed, and then we resume right after the spot where the function invocation happens. See you next time when we add formal parameters. Welcome back. A function can be defined so that it does different things depending on parameter values that are passed to it. For example, here's a definition of the function hello2. The only difference in this function versus our previous hello is that we have another variable name inside the parentheses. We've called it s. That's called a formal parameter name, any variable name inside those parentheses. So sometimes we call it a formal parameter or a parameter name. Then when we invoke the function, down on line 5, we'll pass some string into it. In this case, we're going to pass the string Iman. By the way, that's Iman Yekazare. He's the guy who developed the practice tool that I hope you're using a lot. When we do that invocation, the variable s gets the value Iman at the beginning of the execution of the function. It's like having a behind-the-scenes assignment statement. It's as if we have a line of code that says s equals Iman. And then, in the rest of the execution, we'll be able to refer to the variable s. So let's actually do this using CodeLens. We first create the function and assign it to the name hello2. And then we get to line 5, we're going to invoke the function. But behind the scenes, there was this assignment. S is now bound to Iman. So that when we print hello plus s, we get hello Iman in the output window. And then it says, glad to meet you. And we're done with that invocation. The second time we invoke it, we're going to get s bound to Jackie, because Jackie is the value that's passed in. So now s is bound to Jackie, and we'll get Jackie's greeting appearing in the output window. Hello, Jackie. Often, we'll refer to the parameter values as inputs. Don't confuse that with the input function. Remember, the input function asks the user to type in a value. Here, we're talking about a value that is passed into a function as an input to it. So this Jackie, it's an input to the hello2 function, or sometimes we'll call it an input parameter or a parameter value. A function can take more than one input parameter. Here, the function hello3 has two formal parameters, s and n. We're going to refer to both of those parameters. S we refer to on line 2, n we refer to on line 3. Remember that star, when applied to strings, means to repeatedly concatenate the string together. So the greeting is going to be something like hello way or hello kitty, and we're going to concatenate that together to itself a bunch of times. So it just repeats that string n times. Let's step through that code. We create the string, or we create the function rather, and then we call it. The first time we call it, we're passing in two parameter values, way and for. The very first parameter value automatically gets matched with the first formal parameter name. So we get s bound to way. The second value goes to the second parameter name, so n gets the value 4. We call this positional parameter passing. The first parameter value goes with the first parameter name. Then when we execute on line 2, we'll get a value for greeting that's hello way. And on line 3, we will print that out a bunch of times. You can see down here, we have said hello way 4 times. The next time we execute this, we have s is bound to an empty string, and n is 1. So our greeting is just going to be hello with a couple of spaces. We're going to print that out 1 time, and it looks just like hello on the output because we can't see the spaces. And the last time we invoke this, we've got kitty and 11 as our 2 parameter values, our 2 inputs, and so we get hello kitty, hello kitty, hello kitty 11 times. In summary, formal parameters, sometimes called parameter names or input parameters, those are inside the parentheses in the function definitions. So s and n are our formal parameters. And then we have parameter values, or sometimes they're called arguments or actual parameters. Those go inside the parentheses on the function invocation. They get matched up positionally, first parameter value with first parameter name, second parameter value with second parameter name. The values are bound to those parameter names at the beginning of the function execution with this behind-the-scenes assignment. It's as if we have s equals way and n equals 4, and that those assignment statements are executing behind the scenes at the beginning of the invocation of hello 3. We'll see you next time for functions that produce outputs via return values. Welcome back. One metaphor I find helpful is to think of a function as a machine. It may take some inputs, the parameters, and then when you run it, that's the kind of shaking that you see in this animation, it can produce an output. So let's look at how to make a function return a value. So here's a definition of the square function. Notice line 3. We have a special word, return, and then afterwards any Python expression, in this case just a reference to the variable y. The value of that variable is some Python object, and that's the value that will be returned from the function. Let's take a look at line 6. We're invoking the function square. We're passing in an input, an argument. That's going to be bound to the first formal parameter name, x, and then we'll execute this function. We're going to multiply whatever x is. X is going to be whatever just square was, and we'll multiply it by itself on line 2 and assign it to the variable y. We're going to return a value, and whatever is returned becomes the value of the entire expression, so that is what is going to be bound to the variable result. Note that the word result here is not any kind of special word, that's just a variable name. Return is a special word. That means to return a value from the function. So let's see that in CodeLens. So we first define the square function, then we get to square is bound to the value 10. That happened on line 5. Then on line 6, we're going to invoke the square function. So behind the scenes, we're going to get an assignment that the variable x is going to get whatever value to square had. So to square was 10, and so x is going to have the value 10. We then execute the code that's inside the square function. We get y is 10 times 10, or 100, and then we return y. So the value of this entire expression, square of 2 square, becomes 100, and that is the value that gets assigned to the variable square result. Now, if you were paying close attention there, you will have seen that when we finished the execution of the square function, some of the variables disappeared over here. We had them, and then they disappeared when we finished. We're going to talk more about that in later screencasts. So hold on for some of those details. Now, if a function doesn't have a return statement, it will automatically return a special value called none. Let's see that. Here's an example illustrating a common confusion for students. Printing a value doesn't return that value. So on line 3, we really should have a return statement. In our definition of the square function, we've calculated 10 times 10 or whatever it is, and we should be returning it, but instead we're printing it. If we don't have a return statement at all in the function definition, it's as if we had a statement at the end saying return the special value none. So let's see what's going to happen in this execution. We define the function square, we set to square to have the value 10, and now we invoke the function. X gets as its value, in our behind-the-scenes assignment, X is getting whatever to square had. So X gets the 10 that 2 square was. So X has the value 10, and we execute. Y gets the value 100, and then we print Y. So we can see in the output window we've already printed Y, but we didn't return anything, and so it's as if we have returned the value none. And that means that square result is going to have as its value none. Now you see here, square result has the value none, and that means that when we go to print this formatted statement, the result of something squared is something, we're going to get that the result of 10 squared is none, rather than the result of 10 squared being 100. What we really needed to do was not print, but return y. And then we would have gotten that the result of 10 squared is 100. One other important thing about the return statement. It interrupts the execution of the function. No other code in the function executes after a return statement is executed. If you've played the board game Monopoly, it's like the go to jail move. Do not pass go, do not collect $200. In our case, do not execute any more code inside this function. Even if you're in the middle of a for loop or an if statement, a return statement makes you skip the rest of the code in that function. Now here's an example. We define this function weird. It's not actually useful, but it's going to be very illustrative of how this immediate return works. So lines 1 through 5 define the function. Line 6 invokes it. So when we invoke it and we get to line 2, we'll print out the word here, and then we'll return the value 5. As soon as we return, means we are not going to do anything with the remaining lines of code. They are orphaned. We will not pass go. We will not execute print there. We will return the value 5, and x will have the value 5, and we will print 5. So we do get the here printing. We don't get there. There never shows up in our output, and the 5 is coming from line 8. that's not a very useful function, which is why I called it weird. But let's look at a common programming pattern where return does occur in the middle of a function, and it's a good idea. This function, called longer than 5, returns a Boolean value, true or false. It takes as an input this one formal parameter called list of names. It's expecting that to be a list of strings. If any of those strings has more than 5 characters, the function returns true, and otherwise it returns false. So with list 1, all the names Sam, Tara, Sal, Amita, they're all 5 characters or less, return false, because none of them have a name longer than 5 characters. With list 2, both Lauren and Natalie are names that have more than 5 characters, and so longer than 5 will return true. How does it work? Well, we loop through all of the names. That's what's happening on lines 2 through 5. And if we ever get a long one, if the current name is long, then we will execute line 4, and we will return the value true. As soon as we do that, we're done with the for loop. We're done with everything. Do not pass go. Don't collect $200. Get out of this function and just return the value true. If, however, we manage to get through the entire iteration without ever exiting the function, without ever executing line 4, then we will execute line 6, which says to return false. So the reason this logic works is that we're never going to get to line 6 if any of the names are long. We'll only get to line 6 if we've processed all of the names and none of them caused us to return true. So that means that none of the names were long, and it's safe to return false. So let's see this in CodeLens. We'll go step by step. So we define this function. We invoke it the first time on the list 1, Sam, Tara, Sal, and Amita. So behind the scenes, we get list of names getting bound to that list. Then we're going to start iterating through that list of names. On the first iteration, our variable name is bound to Sam. Is it longer than 5 characters? No, it's not. So we go on and get a new value for name. Name is now bound to Tara. Tara is not long. Sal is not long. Amita is also not long. And now we've iterated through all of the list of names, and we get to line 6, where it says, I guess none of them are long, so let's return false. The second time we invoke it, we get the other list of names, and now when we iterate through, Ray is not longer than 5, Io is not longer than 5, but Lauren is longer than 5, and so finally line 4 executes. We return true. We never even get to look at Natalie, but Lauren was long, and that's enough to know that one of them was too long, and we get an answer of true. So in summary, to return a value from a function, we have the word return, and then some expression that evaluates to a value, in this case, the value false. If we're in the middle of the function and we have a return, we ignore the rest of the code in the function. We exit out of the for loop, we exit out of the if. We don't pass go, we don't collect $200, we're just done with this function. If we have a function that never executes any return statement at all, we will return the special value none. And the other thing to remember is that print is for people. You can use it inside of a function, and it'll generate an output in the output window, but it doesn't cause anything to return from the function. Return is for functions. It doesn't print anything, but it returns a value to the spot where the function was invoked. See you next time. Welcome back for a little Way of the Programmer segment on how to decode a function. Here's a habit that I hope you'll cultivate whenever you see a function definition or whenever you write one. Decode that function definition. Ask yourself 3 questions. First, how many parameters? Second, what types of values will be bound to those parameter names? And third, what is the type of the return value? So let's work through a few examples. Here's a function, CYU3. How many parameters does it have? That's our first question whenever we try to decode a function. And it's the easiest one to answer because you can just look inside the parentheses and you can see that there are 3 variable names separated by commas, so 3 inputs. And that's exactly the question that's being asked. Sure, 3 inputs, x, y, and z. The next question is, what will their types be? So what are the types of x, y, and z? The first question that's asking you is for x and y because it turns out they have to have the same type. How can you tell that? There's nothing in the function declaration that tells you that, so you have to look in the code and see how those variables are used. In particular, we have x minus y in this expression. What are the types of objects that you can do a minus on? And the answer is numbers. They could be integers, they could be floats. Strings, not so much, and not lists either. So let's try that. Integers and floats. Sure enough, we are correct. How about the type of z? Well, we have to look where z is used. And z is used down here in the else. We're running an append method on it. Which kinds of objects can you do append on? And the answer is only lists. Remember that lists are mutable. You can do append. Strings, you're not allowed to. So C is correct. If I had answered D, I'd get a little feedback telling me append can't be performed on strings. And then the final question for decoding a function is, what kind of return value does it give you? And there are 2 spots in this code where we're returning a value, either y minus 2 or x plus 3. We previously inferred that both y and x had to be numbers, either integers or floats. And this doesn't tell us any more about whether they're going to be integers or floats. Minus and plus are both operations that work on both of them. So the return value could either be an integer or a float. Your debugging sessions will be a lot shorter if you can always answer those questions about any function that you're working with. So build the habit, whenever you see a function, decode it by figuring out how many input parameters and what are their types and what kind of value will be returned. See you next time. Welcome back. Let's take a snippet of code that we've seen before and turn it into a function so we can invoke it at any time instead of copying and editing the code. We've seen something like this before. We're trying to eventually get to defining a function total, but here's some code that computes the total of a list, the sum of all the values. And it uses the accumulator pattern. Here we've got a particular list, 1, 5, and 7. We start our accumulator with 0. We iterate through the list, each time updating the total. The accumulator gets its old value plus the current number. So the accumulator Tot starts at 0, and it ends up being 0 plus 1 for 1. 1 plus 5 makes 6. 6 plus 7 makes 13. And we print out 13. Now the question is, how can we make it work for any list of integers rather than just for 157? You can see here that the problem that we're being asked to do is define a function called total, and so we're getting an error because total wasn't even defined. We never created the function called total. So let's do that. Let's define a function called total. And we'll put all of this code inside that function. So we're defining a function total. It's going to have some parameters. We're going to come back to that in a second. And then all of this code we'll put inside here. Now we're going to have to make some adjustments. The first thing is that we want total to take an input. We don't want it to just work on this particular list of 1, 5, and 7. We want it to work on any list. So let's make that be a formal parameter. When the total function gets invoked, that's when 1, 5, 7, or some other list will be specified. So we're going to have that behind-the-scenes assignment to whatever list we want to run this on, rather than having the assignment to a particular value. And then, of course, we need to, let's invoke total. We're going to invoke it and assign the value to a variable called y. Now let's see what happens in CodeLens with this. So we first get the variable total bound to the function. We've defined the function, and now we're invoking it on the list 157. So there's a behind-the-scenes invocation. The variable lst now gets bound to the list 157, and we're ready to execute the lines of code. So we're going to set tot equal to 0, and we're going to iterate. Num is first bound to 1, then it'll get bound to 5, and then to 7. This time it's bound to 1, and tot gets updated to be 0 plus 1. Now num is 5. Tot gets updated to be 1 plus 5, and so on. Now we're printing out that total, and we're returning it. Oops, no we're not. So this is that gotcha that often gets people when they're new to writing functions, that we don't want to print out the total inside the function. We want to return the total. What will happen here is that y is going to be bound to none, when we really wanted y to be bound to 13. So the way to fix that is, instead of printing the total, we're going to return the total. Before I do that, I just want to show you one other thing that's kind of instructive. If I hide CodeLens, if I run this, I'm going to get errors because our function is not right, but I'm also going to get a lot of outputs. And the reason is, and this can be kind of confusing, we have tests when we give you these exercises, for example, writing a function named total. We have some tests where we, behind the scenes, are invoking the function total and checking to make sure that it's giving the right output. So for example, we're invoking it on the list 1, 2, 3, 4, 5, and we're expecting the total to be 15. 1 plus 2 plus 3 plus 4 plus 5. But the actual value that's getting returned is none. And so we're getting an error, but each time we invoke the function, our line 5 is running, and so we're actually printing out the 15. The 13 is coming from our invocation, but the 15 is coming from when there's that behind-the-scenes invocation for the test. Then we have 0 when we invoke it on a list of zeros, and we have another 0 when we invoke it on an empty list. When we have a list of just 2, It's printing out every time, but it's returning the value none, and so our tests are failing. Let's fix that. Let's return tote, and return does not use parentheses. It's a statement, not a function call. Now when we run it, we will pass the tests, and we will not print out anything here in the output window because we had no print statements. If we wanted to print out y, we could get the value 13 to print. So 13 prints, but we don't get any printouts from the rest of the tests. All of those cause the code inside total to run, but it doesn't have any print statements. So we don't get any confusing outputs there. Let's look back at what we did. We started with our accumulation snippet with just one hard-coded list. And just to remind you, so we started with just this hard-coded snippet that worked to find the total of a particular list. Then we converted it to a function definition. The list became a parameter of the function rather than being hard-coded as a particular one. The specific list that we were originally working with became an input, or an actual parameter. It gets bound to the formal parameter. And then we needed to change the print to return. We needed to return the total and print it out here rather than doing a print inside the function. This is a common process for abstracting from a bit of code that works on a particular value. You make that value be a formal parameter name of the function. You pass specific values in when you invoke the function. And the challenge is to make the bit of code inside the function be more general so that it works on any possible input. In this case, any list of numbers. See you next time. Hooray! You now have the tools to write reusable functions rather than just one-off bits of code. You should now be able to define functions with appropriate names for formal parameters, identify formal parameters and parameter values in a code sample, and predict the return value of a function given sample parameter values. I'm going to assume that you've managed to work your way through the exercises we've given you for this lesson, and so, by the power vested in me by the University of Michigan and by Coursera, I hereby dub you programmer, with all the privileges and responsibilities that entails. Let's finish with a joke about functions. Why did the functions stop calling each other? Because they had too many arguments. See you next time. Welcome back. In this lesson, we're going to highlight a few subtleties with functions, including that each execution gets a fresh set of local variables that disappear at the end of the function execution, that functions can call other functions, and that functions can have side effects on mutable objects. At the end of this lesson, you should be able to 1. Avoid the use of global variables in function definitions by creating formal parameters for all values that are needed, and 2. Identify whether a function has any side effects, including mutations to lists and dictionaries. We'll see you at the end. Welcome back. The scope of a variable is the set of statements where a variable name can be accessed. In the function square, on line 2, we assign y to have a value. Since that assignment is inside the function definition, the scope is only the rest of that function definition. On line 6, we really can't refer to y. In fact, we really can't refer to y. We get an error. On line 6, the error message is telling us the name y is not defined. And that's true even though line 2 will already have executed. Line 5 causes the square function to run, so line 2 will have executed. But even so, we say that that variable y was local to the function square. And its scope is local. We can't access it out here on line 6. Now suppose we had a variable y at the top level, outside of any function definition. Say we did y equals 5. Now when we get to line 6, y will be defined, but the value will be 5 and not 100. What we get is the value 5 that we assigned on line 4, and not the value 100 that we would have assigned on line 2. It's going to help to introduce a little vocabulary here, the idea of a namespace. A namespace is an environment where all names are unique. In the city of Ann Arbor, Michigan, we can only have one main street and a single stadium boulevard. But names can be reused in other namespaces. Other cities have a street named Main Street, but it doesn't refer to our street, it refers to theirs. In Python, there is one global or top-level namespace, and then each invocation of a function creates a new namespace. In CodeLens, we show these namespaces as stack frames. There's a global frame where we've defined square and we've defined y, and then we invoke the square function that creates a new stack frame. And CodeLens is nice enough to label it for us. It says, this is the stack frame for the invocation of the square function. The behind-the-scenes assignment, where the formal parameter name x got its value of 10 because we passed in the value 10 for it, that goes into the local stack frame. That's in the local namespace for the invocation of square. Then we set y to be 100. That's also in the local stack frame. So it's really interesting to notice here, we've got y is 5, we've got y is 100. This works just fine because they're different namespaces. Just like we have Main Street in Ann Arbor and Main Street in another city, we can have y in the global frame and y in the local frame. So here's the gory details of how variable lookup and variable assignment work with namespaces. I'm just going to adjust this example slightly. The first rule is if you refer to a variable in the code inside a function, if that variable name is ever assigned a value inside the function definition, even further on in that function definition, then it treats the reference as local. If it finds the value on the local stack frame, it uses that value, and otherwise it's an error. So here, it's going to be an error on line 2. We are referring to the variable y. Y is assigned a value somewhere in the square function, which means that y should be a local variable throughout, but when we are on line 2, y doesn't have a value. It does not go and get the y equals 5 from the global stack frame. It just says y is referenced before assignment on line 2. So that's an error. If, however, the variable name is never assigned a value inside the function definition, then it will look in the global stack frame. Suppose I do w equals q plus 1. Well, let's show it in CodeLens so we can really see what's happening. Define all these variables in the global frame, and now we start running square. So we get to line 2, it tries to look up q. Q is never going to be a local variable in the square function. So therefore, when we look up q, it'll go look it up in the global frame. And we get 7, add 1 to it, and w gets the value 8. So if we look up a reference to a variable, and that variable is ever local inside the function, it's got to look it up only in the local frame. If it's never going to be a local variable in that function, then it looks it up in the global frame. Now this can be pretty confusing, and your programs will be a lot easier to understand if all of your variable references are just references in the local frame. So my recommendation is avoid referring to global variables inside a function definition. Don't do this. It's legal Python, but it's not a good idea. Make another formal parameter for the function and have whatever value you need to get passed in as a parameter to the function. So that's how variable lookups, references, happen inside of functions. What about assignment inside a function? Assignment is always done in the local namespace, the stack frame for that function call. So if we go back to our original code, notice that line 2 creates a variable y on the local stack frame. So there is already a y on the global frame, but when we get to line 2, we create one on the local stack frame. So the rule for assignments is that we're always assigning to a local variable. There actually is a way to force lookup and assignment inside of a function to use the global stack frame. I'm going to show you how to do this for your understanding, but don't do it in your programs. It'll lead to confusing programs that are hard to debug. Other programmers will shun you. You'll have no friends and you'll live a miserable life. Okay, maybe it won't be that bad, but just don't do this. I'm going to show you for your understanding. I can declare y to be global. If I now say w equals y plus 1, again, don't do this, just so you can understand it. Y is 5 on the global frame. We say, please treat y as the global y. Now, line 3 works because we can get to the y equals 5, and w gets to be the value 6. Now we're going to change y in the global frame, and we're going to return our 100. So this is doable, but it leads to very confusing code. That's local and global variables for you. Inside a function definition, variable assignments create local variables. They can't be referenced outside the code for that function, and that includes the formal parameters of the function. Those will also be local variables. Variable references use the local version of the variable. You can reference a global variable inside a function either by explicitly declaring it global or by referencing a variable name that is never assigned a value inside the function. But your life will be better if you never do that and make all of your references to variables inside of functions be local references. We'll see you next time. Welcome back. You've already seen that a function is a useful way to abstract from a bit of code to something that has a name and has parameters. The parameters help to make the code more reusable. You pass in a different parameter value and get a different result. And the name makes it so that you can refer to the whole action of the function with a single name. It makes your code easier to read and understand. In this video, we're going to carry the abstraction process one step further. We're going to decompose what a function does into a set of actions, and some of those actions may be implemented in other functions. We'll just invoke those other named functions. So in other words, inside of a function's code, we're going to invoke another function. For example, here we have a function sum of squares that takes 3 inputs, x, y, and z. It takes the square of each one on lines 6, 7, and 8, and it adds them all up and returns the sum. Now, in order to get the square of each of those inputs, we invoke the square function, which is defined up here. So we're inside the function sum of squares, we're invoking the function square. Let's see that execute in slow motion. So first we define the two functions, and then we set values for A, B, and C. Those all get set in the global frame. And now we're ready to invoke sum of squares. So we get a new stack frame, and we get the values for the parameter names. So X gets whatever A used to be bound to, or still is bound to. So that -5 came from there. Y gets the value that B had, which was 2. Z gets the value that C had, which was 10. Now when we execute sum of squares, we get to line 6. And on line 6, we are invoking the square function. We're invoking that inside of the definition of sum of squares. So when we invoke it, we get another stack frame. So this is going to give us a local namespace for variables for the execution of square. And it's also interesting to note that we have a variable x, whose value is -5. In sum of squares, there's also an x, whose value is -5, but these are different variables. So we could change the value of x in square, and that would not have an effect on sum of squares. In fact, we'll see that because we do a similar thing with the variable y. On line 2, we create a value for y in the square stack frame. So now y has the value 25. There's also a value for y in the sum of squares frame, but it has a different value, 2. And we have not changed anything here. Once we continue the execution, we'll go forward. The square stack frame is going to disappear. We're going to return the value 25, but the y in sum of squares is completely unaffected. That explains the mechanics. Now let's try doing functional decomposition to write a little bit more useful function. Remember from last week when Steve taught you about dictionaries? You had some code to accumulate a dictionary of counts. I've turned that into a function, countFreqs, short for count frequencies. It takes one formal parameter, st, short for string, to remind me that the input parameter is going to be a string, and it's going to count frequencies for whatever string is passed in. Now the code should look a little bit familiar. From last week, we start by making an empty dictionary. We iterate through all of the characters in the string. If the character is not yet a key in the dictionary, meaning this is our first time seeing it, we add it as a key in the dictionary, and we give it an initial value of 0. Then, regardless of whether we've seen this character before or not, we're going to increment the counter that's associated with it. So if this was the first time we saw it, it starts with a 0, and now it's got 1 for its count. But if we've already seen this character, say, 3 times before, the count will get updated to be 4. So the new things here over what you saw last week are that we've turned the bit of code into a function. And before you just saw how to do this with a particular string, now we're making it work for any string. We've made the string be a formal parameter of the function. And the other thing that's different is instead of printing out the result at the end or assigning it to a variable, we just return it. And then whatever code is invoking countFreqs will decide what to do with the return value. Similarly, you had code last week given a dictionary to find the best key in the dictionary, to find the key that had the maximum value associated with it. So again, I've turned that into a function. I called it best key, and it will take any dictionary as an input. That dictionary should have keys and values, where the values are numbers, and it's going to return the key that has the highest value. Given both of these functions, countFreq and bestKey, I can now compose a bigger function, mostCommonLetter. So it's going to take a string as an input, and just to distinguish it, I've chosen to give it a different parameter name. I could have called it st just like I used for countFreq, but I decided to call it s here. And we're doing this in two steps. In step 1, we count the frequencies in s, which creates a dictionary, and I've assigned that to a variable called frequencies. I pass that dictionary into the bestKey function, and what I get back is one key, the key that has the highest value. I return that, and that should be the most common letter in our string s. So let's run this and make sure that it actually works. Down at the bottom, I'm invoking most common letter on line 21, and I'm passing in a string that has a bunch of B's, a bunch of C's. You can see that it's got more B's than any of the other letters, and what we should get as our output is just the letter B. And sure enough, that's what we get. If I change my string and give it a whole lot more C's, now when I run it, I should get the letter C instead. And sure enough, I do. Now, I've described this as a composition process. Often, though, you'll actually solve problems in the opposite order by decomposition. You might start by saying, hey, I want to find the most common letter. So let's decompose that into first finding the frequencies of all the letters and then picking the one with the highest frequency. When I start that decomposition process, those functions may not exist yet, but I just refer to them by name, and then afterwards I fill in definitions for them. So really, how I wrote this code, I started by defining most common letter, and I referred to the functions countFreq and bestKey, even though those functions didn't exist. Because I'd given them names that made me know what they would do, I was able to write that function and have it be clear what it was going to do, and then I had to go and fill in the other two functions. As a little aside, you may be wondering why it works to have on line 2 a reference to the countFreq function which has not been defined yet. When we talk about executing Python code from top to bottom, so we shouldn't be able to refer on line 2 to a function that isn't defined until line 5. The reason we don't get an undefined variable error is that even though on line 2 we're referring to countFreq, we don't actually execute line 2 until after we invoke on line 21 the most common letter function. So by the time we actually execute line 2, countFreq has been defined. If we were not inside a function definition, we really would have a problem. For example, if I say print of x and then x equals 4, I will get an error because on line 1, x is not defined. The difference is that inside a function, we're not actually going to refer on line 5 to countFreq until line 5 executes, and by that time, the countFreq function has been defined. So to summarize, functions can call other functions. It's called composition. You get multiple stack frames when that executes. Each one has its own namespace and its own local variables. As a problem-solving strategy, it's helpful to decompose. Define a function by referring to other functions that don't yet exist, and then write those functions. See you next time. Welcome back. There's one more tricky thing that we want you to be able to reason about with functions. It's called side effects. If a function makes a change to a mutable object, like a list or a dictionary, that's called a side effect. The vocabulary here is that the main effect of a function is the value it returns, and any other lasting impact that it has is a side effect. One other thing that I'll refer to as a side effect is printing something out in the output window. Let's see a side effect of mutating a list. First, this code gives us a little reminder that variables are local. So we create these two functions. We make a local variable y, that's in the global frame, and then we invoke the double function. The double function takes as input some value which it assigns to a formal parameter y. So notice that we have a different y. They happen to have the same value, but they are completely different variables here. And then we're going to assign, on line 2 of the code, a new value for y. Watch what happens in the double stack frame. It's not going to affect what happens in the global frame. So when we execute line 2, in the double frame, y now has the value 10. That did not have any effect in the global frame. You might also have noticed that the double function doesn't have a return statement, and therefore it returns the value none. It doesn't actually matter in this case because we don't do anything with the value of double. We're not assigning it to anything. When we do finally get to line 10, and we're going to print out the value y, we get the value y from the global frame. So it's the value 5 that's going to print out, not the 10 that we had in the local frame for the double function. And sure enough, we get the value 5. Now that was just a reminder that we have local variables, and changing a local variable doesn't affect the global variable. But our next lesson is that even though we don't affect a global variable, we might affect a value that is shared by a local variable and a global variable. So variables are local, but objects are not. Here we're going to see that we mutate an object inside a function and it stays mutated. On line number 12, we've created a list with 4 elements, our students. On line 12, we've created a list called myList. Its value is this list of 4 strings. Our students are awesome. That's you. And then we're calling changeIt. On line 13, we call changeIt. That creates a new stack frame for the changeIt function. And its formal parameter, LST, gets a value. The value it gets is whatever myList had as its value. Well, myList was pointing to that list object, and so the LST variable in the changeIt stack frame, that LST variable also points to the same list. This is important because now when we get to line number 5, list square bracket 0 gets a different value. Instead of being our, it becomes Michigan. And instead of students, we get Wolverines. So notice that myList and list, these are still 2 different variables, but because they're aliases for the same list, when we finish this execution and then we print myList, myList has the mutated value. The variable myList is pointing to the object which has been mutated, and we get Michigan Wolverines are awesome instead of our students are awesome. So we call this a side effect. The changeIt function is having a side effect on the list object. Just as we talked about earlier when we first introduced the idea of multiple aliases for the same list object, this can get confusing if you're not careful. Sometimes it's clear that a function is going to have side effects and you expect it, but sometimes you'll be surprised and debugging can get difficult. What happened to my list, you'll ask? To avoid potential confusion, it's best to just avoid side effects in your functions whenever you can. If functions never ever have side effects, that's a style called functional programming. There are programming languages built around that principle. of functional programming, but Python is more flexible, and we will sometimes make use of side effects, but you should do it sparingly and consciously. See you next time. Phew! You've now seen some of the subtleties of passing parameters, accessing global variables, don't do it, functions calling other functions, and functions having side effects. You should now be able to avoid the use of global variables in function definitions by creating formal parameters for all values that are needed. And you should be able to identify whether a function has any side effects, including mutations to lists and dictionaries. As much as possible, I encourage you to avoid side effects. Come as close to strict functional programming as you can. Speaking of functional programming, why did the functional program return her TV? Because she kept muting the sound by accident. She returned the TV and asked for one that was immutable. Okay, that one was a stretch. We'll see you next time. Welcome back. This will be a short lesson. I just want to introduce a cool feature, packing and unpacking. It doesn't really let you do anything new, but it lets your code be a little more readable. At the end of this lesson, you should be able to, 1, recognize when code is using implicit tuple packing, and use implicit tuple packing to return multiple values from a function. And you should be able to read and write code that unpacks a tuple into multiple variables. See you at the end. Welcome back. In many places where the Python interpreter is expecting a single value, but the code provides multiple expressions separated by commas, it automatically packs all those values into a single tuple. This is just a convenience that makes the code look a little nicer. It looks like you're working with multiple values, when really it's just making one tuple out of them. For example, in this code, we have several pieces of information about an actor, Julia Roberts, and a movie she was in, Duplicity. We can explicitly make those different pieces of information into a tuple using parentheses like we do on line number 1. So we have open parenthesis there, close parenthesis. This is our usual way of creating a tuple. In between, we have a bunch of values. There's Julia Roberts, 1967. All of these values are separated by commas to indicate where one expression ends and another begins. So that's the syntax that you've already seen for creating tuples. It turns out that line 3 does exactly the same thing. It's exactly the same except that we've left out the parentheses. No more parentheses here. And it implicitly reads that as, oh, we got a bunch of values, we got to pack it into a tuple. On line 4, you can see, as with any tuple, Julia is the name of a variable. We look up its value is a tuple. Square bracket 4 says, go and get the 5th item. So Julia is 1, 2, 3, 4, 5. So what prints out here should be 2009. So lines 1 and line 3 are just synonyms for each other. Line 3 is just a way that maybe looks a little bit better as if you have multiple values. One place where this is especially useful is when a function wants to return multiple values. For example, in this code, circleinfo is a function, and it wants to return 2 values, the circumference of the circle and the area of the circle. You can only return one value from a Python function, but that value can be a tuple, as we've done here. So that works fine. I can print the circle information of a circle with radius 10, and it has a circumference of 62.83 and an area of 314. But I also have the option, if I think it looks better, to leave the parentheses out. and it will automatically return a tuple, and I'll get exactly the same output. There you go. So that's tuple packing. We'll see you next time for unpacking. Welcome back. Last time you saw that on the right side of an assignment statement, multiple expressions separated by commas will be automatically packed into a tuple. So line 1, the variable Julia gets bound to a tuple. Square bracket 0 will be Julia. Square bracket 1 will be Roberts, and so on. But instead of referring to the elements of that tuple with square bracket 0 and square bracket 1, we can unpack them all at once into a bunch of different variable names. So we've put a bunch of variable names here on the left side, and what that does, it's as if we've said name equals Julia, square bracket 0, surname equals Julia, square brackets 1, and so on. So it's just going to take Julia, which is a tuple, and take all of the values from that and put the first value that goes positionally, just like we do when we're calling functions. The first value goes to the first variable name, the second value goes to the second variable name, and so on. Notice, however, that the number of variable names on the left-hand side of the assignment statement has to equal the number of values that are on the right-hand side. If I run A, B, C, D equals 1, 2, 3, I will get an error. We need more than 3 values to unpack on line 1 because we have 4 variable names. So if I have 4 variable names, that'll be better. It works. But if I have 5 variable names, I also get an error. Too many values, not enough variable names. There's even a way to pass a tuple to a function and have them automatically unpacked into the parameter names. In this code, we've defined a function add that just returns the sum of its 2 inputs. If I say to add 3 and 4, that will give me 7. Now I can take 5 and 4 and I can tell the add function to get your values from the tuple z. On line 6, I'm saying to add the contents of the tuple z, and it unpacks the first element of z into the variable x. So x gets 5, y gets 4, and we see that 9 prints out. Now I had to do a special little notation, this asterisk, in order to tell the Python interpreter that I wanted z to be treated as a tuple whose components would be unpacked and assigned to the 2 parameter names x and y. If instead I tried to just say add of z, I'm going to get an error because what it's going to try to do is treat z as a single value, assign that value to x, and then it looks for what value should I give to y, and there's nothing for y. So I get an error here. Add takes exactly 2 arguments. It has 2 parameter names x and y. That's what the error message is telling us, but only one was given. We only gave it a single value, the tuple 5, 4. That didn't work. There was no problem on line 6, though, because the star z said, hey, even though it's a single value, a tuple 5, 4, you should unpack that value, and 5 should go for the first variable name, and 4 should go for the second one. Unpacking is particularly useful for making iteration code more readable. For example, when you iterate over a list of tuples. In this code, we iterate over the key value pairs in a dictionary. So we ask for all of the items from D. So that's going to give us a tuple with K1 and 3, and then another tuple with K2 and 7, and so on. We get a sequence of all of these, and we're iterating through that sequence. So at line 4, the value of P will be one of these tuples. And we can ask for P square bracket 0 to get K1, and P square bracket 1 to get 3. Well, let's see what happens when that runs. We have this key K1, value 3. That's coming from the first tuple. Remember, we have this format string where we're substituting in P square bracket 0 there, so we get key colon, and then we're substituting in K1, and then just the word value colon, and we substitute in whatever P square bracket 1 is at this point in the string, so we get the 3. On the next iteration, P is bound to K2 and 7, and so we get key colon K2 value colon 7. Reading that code is a little hard because you have to remember that when you're using this P square bracket 0, let's see, P was a tuple. That tuple was representing a key value pair in the dictionary, and therefore P square bracket 0 must be the key. We can use mnemonic variable names to help us make that a little bit more readable. Well, let's do this in 2 steps. Suppose I say K equals P square bracket 0 and V equals P square bracket 1. Then I can K and V here. And this is just if I pick a good variable name like K for representing a key and V for representing a value, it's easier to read line 6 and remember that what I'm printing out is the key and the value. And once we have that idea, we can go even farther, and instead of unpacking ourselves on line 4 and 5, we can have Python do it for us. So we can stick 2 variable names here, K comma V, and it's going to automatically take each item and unpack it into the 2 variables K and V. This is going to give me exactly the same result. So that's unpacking. You've got one tuple and multiple variable names. The tuple has to have the same number of values as the number of variable names. We can do that with explicit assignment, where there's an equal sign, or we can do it when there's behind-the-scenes assignment, like iterator variables in a for loop. As you've seen here, K and V are having sort of a behind-the-scenes assignment to a tuple, and we're getting them to get unpacked into the 2 variable names K and V. There's also behind-the-scenes assignment whenever you have parameter names in a function, and we can also do the automatic unpacking there, but that requires you to use the star notation to tell Python to do the unpacking. We'll see you next time. Well, that was quick. You now know how to recognize when code is using implicit tuple packing, use implicit tuple packing yourself to return multiple values from a function, and read and write code that unpacks a tuple into multiple variables. For a quick lesson, a quick joke. You know what I love doing more than anything? Trying to pack myself into a small suitcase. I can hardly contain myself. See you next time.
Welcome back. So you've already seen the for loop as a way to iterate over every item in a sequence. A while loop is a much more general way of iterating. So a while loop is kind of like a hybrid between a for statement and an if statement. So a while loop looks like this. You say while, and then just like an if statement, you have a conditional that comes after the while. And then you have a piece of code that will run if this condition is true. But unlike an if statement, where after you're done running this piece of code, if you use a while instead, then by the time you get to this end of code, then we loop back up here and check now is this condition still true. So in the sense that it loops back up to the top, that's kind of like a for statement. So again, when we get to a while statement, we check is this condition true? If the condition is true, then we run this piece of code, and then we go back up and check is this condition still true? So if this condition is not true, just like an if statement, then we skip this block of code and execute the next code block. So let's see this in action. So here I have some code that's going to take the sum of numbers 1 plus 2 plus 3 plus whatever n we pass in. So here we pass in a number called a bound as an argument to our sum2 function. And we're using a while loop in order to do this. So on line 11, we print out the value of sum2 4, which should be 1 plus 2 plus 3 plus 4, which is going to give us 10. And then here we print out the sum2 1000, which is going to be a much larger number. So first I'm just going to run my code just to make sure that it still works correctly. And good, so I see I get 10 here, and I get this number from line 13. Okay, so now that we've done that, let's look a little bit at how it works. So you see that we initialize two variables here. So we start out the sum to be 0, and this is going to be kind of akin to our accumulator variable. So what it's going to keep track of is the sum so far. And then we have this other variable, which we call a number, and what this is going to keep track of is where we are. And that's going to start out as 1, but then we're going to set it to 2, to 3, and then so on until we get to n, which in this case is a bound. So now here we have a while statement, and our condition is while a number is less than or equal to a bound. Again, a bound here is whatever we're adding up to. So as long as our a number variable is less than or equal to a bound, then what we do is we first say the sum equals its previous value plus a number. So when a number starts out as 1, then the sum is going to be 0 plus 1, which is going to be 1. So then after that, what we do is we say a number equals a number plus 1. Again, a number keeps track of where we are. So a number is going to start out as 1, and then it's going to go to 2, and then 3, and then 4, and so on until a number is less than or equal to a bound. Again, a bound here is the number that we're adding up to. So it's going to keep going up by 1 until we get to a bound. And as we're doing that, as we're incrementing this a number, then we're adding that number to the sum that we have so far. And then by the time this while loop is done running, the sum is going to have the correct answer. But let's inspect this code just to make it a little bit more clear. So I'm going to open up CodeLens, and here I have the same piece of code, except I'm only printing out sum2 when called with 4. So the first thing that we're going to do is evaluate the function, so we can see that sum2 is the function that we declared right here. And then we print out the value of sum2 when called with 4. So What that means is that a bound is going to have the value 4. And then we start out the sum with value 0 and a number with 1. Remember, the sum keeps track of the sum so far, and a number keeps track of where we are. And now we're at the important bit, the while loop. Again, we say while a number is less than or equal to a bound. The first time that we run this, a number has the value 1. 1 is less than or equal to a bound, which is 4. And so yes, we do run this code. So in this code, we say the sum equals the sum plus a number. So the sum is going to go from 0 to 1. And then we say a number is a number plus 1. So it goes from 1 to 2. Now the next time we run this, we check, is a number still less than or equal to a bound? So in this case, a number is now 2. And we ask, is 2 less than or equal to 4? Yes, it is. And so we run the code in here, and we say the sum equals the sum plus a number. A number is now 2, so the sum is going to go from 1 to 3. So the sum is now 3, and then a number gets its previous value plus 1, so a number is going to go from 2 to 3. And we ask again, is a number less than or equal to a bound? Yes, 3 is less than or equal to 4, so we run this code. So the sum goes from 3 to 3 plus a number, which is 3, so the sum goes to 6. And a number is going to go from 3 to 4. And then we ask, is 4 less than or equal to 4? Yes, it is. So the sum is going to go from 6 to 6 plus 4, or 10. And a number is going to go from 4 to 4 plus 1, or 5. And now, here's another key point. So now a number is 5. And when we ask, is 5 less than or equal to 4? It is not. So this condition is false, meaning that we're done running our while loop. And we can see that the sum here has the value that we actually want. So now, when we're done running our while loop, we skip to line 9, which returns the sum, and we get 10, which is the correct answer. So let's answer a few questions. First, true or false? You can rewrite any for loop as a while loop. Well, this is true. A while loop is a much more general form of iteration. It's capable of expressing what you can express in a for loop and more, as we'll see in a bit. This question asks, which type of loop can be used to perform the following iteration? You choose a positive integer at random and then print out the numbers 1 up to and including the selected integer. In this case, we could actually use a for loop if we wanted to, because we could use the range function. And anytime you can use a for loop, you could also use a while loop. So I'm going to say here that the answer is A. In this question, we're asked to write a while loop that's initialized to 0 and stops at 15 if the counter is an even number. Append the counter to a list called even nums. So I'm going to say count equals 0, and I want it to stop at 15, so I'll say while count is less than or equal to 15. And I'm just going to say count equals count plus 1. So what we're doing in this code is we're initializing count to be 0, and then inside of the while loop, as long as count is less than 15, we assign its value to its previous value plus 1. So count is going to go from 0 to 1 to 2 to 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15. And then it does get assigned to 16, but as soon as it's 16, then we exit this while loop because 16 is not less than or equal to 15. And so by the time we're done with this while loop, count is going to be 16. Now, this question is asking us to do a little bit more. It's saying if the counter is an even number, append the counter to a list called even nums. So I can check if counter is an even number by saying if count modulo 2 is 0. Again, that's just saying if the remainder when divided by 2 is 0. And what we want to do then is we want to append it to this list, which I'll call Eve nums. I want it to start out as an empty list, and if count is even, I want to say Eve nums dot append count. So let's test our code to be sure that it works. Okay, so we can see that now our code passes all of the tests, and even nums has the value 0, 2, 4, 6, 8, and so on to 14. This question says, below we've provided a for loop that sums all of the elements of list 1. Write code that accomplishes the same tasks, but instead uses a while loop. Assign the accumulator variable to the name accum. So the strategy that we're going to take in order to do this is we're going to have one variable that's going to keep track of the current index. So I'm going to call that variable idx. idx is going to be 0, and then 1, and then 2, 3, 4, 5, 6. And then by the time it's 7, we want it to stop because there isn't a 7th item. So let's write the code to properly set idx first. I'm going to say idx equals 0, and I'll say while idx is less than the length of list 1, then idx equals idx plus 1. Now an important point here is that I said while idx is less than the length of list 1, and I initialized it to 0. So why did I do both of these things? Well, first, I initialized it to 0 because, again, lists and sequences are 0 indexed, meaning that we have to start out at 0 to get the first item. Now, I said less than the length of list 1 rather than less than or equal to because here, list 1 is 1, 2, 3, 4, 5, 6, 7 items long, so the length of list 1 is 7, but we only want to go until the last item. And because we're 0 indexed, we have the last item is actually item 6. So by the time we get to idx equals 7, then we want to break out of this loop. We only want idx to be 0, 1, 2, 3, 4, 5, 6. So I'm going to say less than the length of this list, not less than or equal to. Okay, now we don't just want to loop through all of the indices of this list. We also want to assign a new variable, accum, to be the sum of every item. So I'm going to start out accum equals 0 to say that we haven't seen anything so far. And then just like on line 6 here, where we say total equals total plus the value of that element, I want to say accum equals accum, and then I want to say plus the value at index idx. And I get that by saying list 1 sub idx. So when idx is 0, this is going to be 8. When idx is 1, this is going to be 3, and so on. So again, as idx iterates through all of the indices, this is going to be the value at that index. And so we add the value at that index to the previously accumulated value. Now let's run our code and be sure that it's correct. So we can see that our code works as we wanted it to. That's all for now. Until next time. The listener loop is one of the most common patterns that you'll encounter when using while loops. What the listener loop is essentially a pattern that waits for some input or some value before deciding to terminate the loop. So you can only use while loops with the listener loop because by definition, a listener loop doesn't necessarily know how many times it's going to run. Even after your program starts, you don't know how many times you're going to actually have to execute the code in a while loop. So for example, what this piece of code does is it keeps asking the user for a next number to add up. So it's going to ask the user for input, and then it asks the user to enter 0 if there are no more numbers to enter. So again, before we run this program, we have no way of knowing how many numbers the user is actually going to input, and so we can't use a for loop. We instead need to use a while loop, and we need to say, while the user has not entered the number 0. So let's look at this code. In this code, again, we're adding up the numbers that the user inputs. We're going to add those numbers into this variable, the sum. The sum is going to start out as 0, and then we're going to use another variable, x, to store what the user put in. Here we're just going to arbitrarily initialize x to be -1. The reason that we do that is because in our while loop we say if x is not equal to 0, so if we started x out as 0, then we would skip our while loop. So in our while loop, we assign x to be whatever the user inputted, but we cast it to be an integer. So x is going to be an integer representing whatever the user just entered, and then we add that value to the previous value of the sum and reassign the sum. In other words, we add x to the sum. Now, when the user has had enough numbers that they've entered and they enter 0, then we're going to exit this while loop and we're going to print out the sum. So let's run our code. So here we're asked, what's the next number to add up? I'm going to say 10. And then the next number to add up, I'll say 20. And then I've entered 10 and 20, so that's enough for me. So I'm just going to say 0 to say that there are no more numbers. And when I do that, then I can see that I get the sum of 10 and 20 is 30. I can do this any number of times. So I can do 5, 4, 3, 2, 1, and then 0. And I'm going to get 15. And again, Python isn't going to know how many numbers we actually add up before entering 0, which is why we need to use a while loop here. So this pattern is called the listener loop pattern. Again, we're kind of listening for a particular input. In this case, we're listening for the input is x equal to 0. And while that input is anything other than the termination value, then we keep running our code in the while loop. Let's look at a slightly more complex example. In this code, what we're going to do is we're just going to ask the user if they like lima beans, and we ask them to enter y for yes or n for no. But here's the problem. When the user inputs a value for whether they like lima beans or not, then they could input anything. They could put in a number, they could put in any other letter, but what we really want is for them to enter y or n. So what we're going to do is we're going to keep asking them for a valid input until they enter either y or n. And then by the time that they've produced a valid input, if they say y, then we print out great, they are very healthy. If not, then we print out too bad. So let's run our code first to see what we're actually running. So again, we ask, do you like lima beans, y or n? I'm going to put in something else. Now when I hit OK, then I'm going to get this prompt again, and it's going to say, do you like lima beans, yes or no? So I'm going to enter something else, and I'm going to keep getting this prompt until I enter either y or n. I'm going to say y for yes, and I get great, they are very healthy. So a couple of notes here. So first, all of these print statements appeared kind of suddenly because of a kind of quirk in the interpreter that we actually use. These should have been printed out as I was inputting numbers. The important thing to focus on here in the output is that we printed out great, they are healthy, when I finally entered y for yes. Okay, so the important part of this code is this function, get yes or no. What this function does is it's going to keep pestering the user until they enter in either y for yes or n for no. If they enter in any other invalid input, then it's going to ask them again for input. So in this code, we first create a variable that keeps track of whether their input is valid. We initialize that to be false because the user hasn't actually put in anything. And then we say, while the user's input is not valid, then ask the user for an answer. and we assign that to the variable answer. We then convert that to be uppercase, so lowercase y gets converted to capital Y, lowercase n gets converted to capital N. And then we say, if answer is either of the valid possible inputs, either capital Y or capital N, then we assign valid input to be true. And what that means is that the next time we actually go through this while loop, valid input is true. And so not true is going to be false. And false is actually good in this case because that means we're breaking out of the while loop and returning whatever the user answered. If the input is not valid, then we instead print out, please enter Y for yes or N for no. That's what gets printed out here. And then we go back up to the top of this loop and we say while not valid input is going to be false, meaning that not valid input is going to be true, meaning that we're going to ask the user again to enter in Y or N. So as long as the user enters anything other than Y or N, then this while loop is going to keep asking them to enter in yes or no, until they actually enter in Y or N, in which case we're going to return what they entered. That's all for now. Until next time. Welcome back. Break and continue are two special kinds of statements that can be used within while or for loops. A break statement breaks out of whatever loop contains it. So here, if we're within a loop and we encounter a break statement, then Python is going to break out of the loop immediately. So this break statement is going to say that the program should jump from here to here, and it's going to skip the rest of whatever is in the body of the for loop, and it's not even going to check the condition again. A continue statement is similar. A continue statement, like a break statement, does skip whatever is in the rest of the loop, so it's not going to run this code. But unlike a break statement, which takes us to the bottom of the loop, a continue statement instead says to continue at the top of the loop, and so it's going to check this condition once more. So let's see what break and continue statements do in code. So here we have a while loop. This condition is true, meaning it's always going to be, well, true. So what that means is that without a break statement, then this is almost by definition going to be an infinite loop. But here, in the body of the loop, we first print out this phrase will always print, and then we call break, and then we say print does this phrase print, and then here we print out we're done with the while loop. So I want you to think a little bit about what this code is actually going to print. So what I expect to happen is that when we run this code, even though this says while true, this is only going to print out once, because after this prints out, then we break out of our while loop. And then we skip what's here because that comes after the break, and then we print out we're done with the while loop. So I expect this and this to print out. Let's run our code to be sure that that's the case. So you can see the only things that print out are this statement and this statement. Now, what would happen if I replaced the break with a continue? So when I run this code, what I should expect is that it's going to get stuck in an infinite loop. The reason is that we, on line 2, print out this phrase will always print, and then this continue statement jumps to the top of the loop and checks the condition again. And here, this condition, again by definition, is going to be true, and so we're going to print this out again and then continue. And so we have an infinite loop, and I would expect this phrase will always print to be printed out, well, a huge number of times before our program actually stops terminating. And you can see when we look at our code that that's exactly what happened. So let's look at another example to see how a continue statement works. So here we have a slightly more complicated piece of code. We have a number x, which we set to 0, and then we say while x is less than 10, And as long as x is less than 10, we print out we are incrementing x. Now, what we do is we say if x is even, so in other words, if x modulo 2 is 0, then we add 3 to the value of x. So x would jump from 0 to 3, and then we say continue, which takes us back to the top of this for loop. Then we say if x modulo 3 is 0, in other words, if x is divisible by 3, then we assign x to be x's value plus 5, and almost regardless, then we add 1 to x. And by the time we're done, we print out done and we print out the value of x. Now, let's run this code in CodeLens to see what happens. So again, we start x as 0, and we say while x is less than 10, print out we're incrementing x. Here, x is divisible by 2, so x is going to jump from 0 to 3. Now again, when we hit this continue statement, we're going to go to the top of this while loop. So we jump back up to the top. We ask, is 3 less than 10? Yes, it is. In this case, 3 is not an even number, so we check, is it divisible by 3? Which it is, and so we add 5 to x, and then we add 1 more onto x, and so x ends up with the value 9. 9 is less than 10, so we print out we're incrementing x. 9 is not even, but it is divisible by 3, so x gets the value 14, and then 15, and then now when we check our condition, 15 is not less than 10, so we say we're done with our loop, and x has the final value of 15. So again, here we used a continue statement to ensure that we weren't going to run what was in the rest of this loop. We instead jumped to the top of the while loop. That's all for now. Until next time. Welcome back. So as we talked about before, a while loop is generally more capable than a for loop, but there are a few drawbacks to using while loops. The first is that it can be a little bit more tedious to express the same concept, as you might have seen in some of the code samples from before. But the second is that you can get stuck in what's called an infinite loop. An infinite loop is a loop that never terminates. In other words, your program, if it could, would keep running forever. Now, remember that if we have a while loop like this, then every while loop has a condition. And by the time we get to the end of the while loop, then we're going to go back to the top and check if this condition is still true. And what that means is that if you ever run the code in this while loop, then it better have a chance of switching this condition from false to true. But if that's not the case, in other words, if this condition is always true, and we always reach the end of this while loop, then our code is going to be stuck in what's called an infinite loop. Because if we always reach the end of this while loop, then we're always going to go back to the top, and if this condition is always true, then we're always going to run this code once more. And that's called an infinite loop because your program would keep running infinitely if it could. In reality, this textbook has a mechanism to prevent your code from running too long, and pretty much every interpreter has some way of breaking out of an infinite loop, but they can be frustrating nonetheless, and they're important to be able to recognize. Now, this code is actually stuck in an infinite loop. So if I ran my code, and I would see first that my cursor is stuck on a pointer, so that tells me that something's wrong. If I even try to click or type anything, then I'm not going to be able to, because this computer is working so hard trying to run this little while loop that has 3 lines. Now, after a while, then the Python interpreter is going to say that this code ran too long, but until then, I'm not going to be able to do anything on the page. So as it's evaluating this, let's try to analyze why we're actually stuck in an infinite loop. So here we go. The code finally finished running, and you can see that it printed out bugs many, many times. So I'm going to scroll to the bottom here. You can see that it printed out bugs a lot. And at the end, I'm going to get a message that this program exceeded the runtime limit. So in other words, this program tried to run for too long, and this probably indicates that your program is stuck in an infinite loop. So let's look at why this program is stuck in an infinite loop. So here we initialize a variable b to be 15. So that looks good so far, and we say while b is less than 60. Okay, so this condition is of course going to be true while b is 15. So when b is 15, then we're going to run this code. And then we say b equals 5. Well, that looks a little bit out of place, but let's come back to it in a little bit. On line 5, we print out bugs, which as you can see, gets printed out a lot because this while loop is run a lot. And then on line 6, we say b equals its previous value plus 7. Now, let's come back to this line, b equals 5. Because what assigning b equal to 5 does here is it kind of resets the value of b. So again, our check is if b is less than 60. And so if we keep resetting b to be 5, even if we increment its value to be 12 later on by adding 7 to it, then b is still always going to be less than 60 because every time we run this loop, we reset b's value to 5. So maybe if line 4 was accidental, so if we commented it out, then we would actually be able to run our code. So again, the problem here was that we were resetting b to be 5 every time we ran this code. So it's important to be able to recognize how infinite loops occur. They can occur in many, many ways. So this example is just one of many ways to accidentally write an infinite loop. As you get more experience in writing while loops, you'll become more adept at being able to identify and fix infinite loops. That's all for now. Until next time. The fact that optional parameters' default values are only evaluated once can lead to some unintuitive outcomes. So here we define a function that has two arguments, a and L. L's default value is an empty list. Now, note again that because this value is only evaluated once, what that means is that we have an empty list that lives somewhere in the frames and objects as the default value for L. So here, after we define our function f, then we first print out f called with the value 1. Now, in the body of f, we actually mutate the value of L. So what that means is that when we call f on line 5, we pass in 1 for a, and L is going to be that empty list that we created right here. When we run line 2 to say L.append a, then we append 1 to our empty list, and now our list is a list that has one item whose value is 1. And now on line 3, we return that list L, but the thing to note here is that even though this list is going to go away in code lines, it actually keeps its value of a list that has one item whose value is 1. So even though this disappears in code lines, by the time we get to line 6, this list still has the value 1. So now on line 6, when we call f with a equals 2, then you can see that L is this list that has one item in it already. So now on line 2, when we append a to our list, we add 2 onto this list. So we're going to say list is now a list that has 1 and 2 in it. And so if we kept calling our function f to add new values to our list, then we would get a longer and longer list as our default value for L. So here, by the time we get to line 7 and we call f with 3, then when we call this function, our list L already has 2 values in it, and on line 2, we add 3 on as a third value in our list. So the important thing to note again here is that as our default value gets mutated, it affects future calls to this function f. Now, an important distinction here is distinguishing between lists that are different objects but have the same value versus this list, which is the same object. So for example, on lines 8 and 9, we pass in two different values for L. On line 8, we pass in a list that has the string hello as its one item. On line 9, we pass in a list that looks identical, but because these are separate expressions, then these are actually separate objects. What that means is that by the time we get to line 8, and we print out the value of f called with a equals 4 and L equals the list with the item hello, then when we actually call L dot append a, then we're mutating this list, and that has no effect on this list. So here we're mutating this list to add 4 onto it, which you can see here. And then when we get to line 9, then we're mutating a different list. So note again here that we have a list whose only value is hello. It doesn't have the 4 that we added on to this list. That's all for now. Until next time. Keyword parameters are closely tied with optional parameters. So here we have our function f that takes in 3 arguments, x, y, and z, and y and z have default values of 3 and 7. Now here on line 5 we can see that we can call our function by only providing x, and then y and z get their default values. On line 6 here, we call our function with x equals 2 and y equals 5, and z getting its default value. But suppose we wanted to call our function and provide a value for x and z without actually passing in a value for y. So in other words, we want to give y whatever its default value should be. So if we wanted to do this, we would want to kind of skip a value for y. If we tried to do something like skipping y by saying 2 comma blank comma 8, then we would get a syntax error because Python doesn't understand this format. Instead, what we can do is we can use a keyword parameter. So rather than skipping an argument, we can just say that this 8 is intended to be the value for z. And we do that by saying z equals 8 when we call our function. Now, what this does is x gets the value 2, and z gets the value 8, and we never specified a value for y, so y gets its value 3. And when we run our code, we can see that in this second call here, that this is the case. So again, x is 2, z is 8, and then y, it's its default value. So these are keyword arguments. We could also do this for x. So we could say x equals 2 and z equals 8, and this would have the same outcome. And the nice thing about keyword arguments is that they allow us to put our arguments in any order. So here I'll say x equals 20 and z equals 8, but I'll specify z before I specify x. Now, note that keyword arguments aren't going to give arguments that don't have default values. So for example, if I tried to call our function f and just specified z equals 8, then we haven't passed in anything for x, and we get an error because we haven't actually specified what x is. So if we wanted to do this, we would have to specify a value for x somewhere, or we would need to give x a default value in our function definition. So it's also possible to accidentally specify multiple values for the same argument here. So the easy case to see it would be if we specified z equals 8 and then z equals 4. If we did that, we would see that we have a keyword argument repeated on line 5. It's less easy to see if we accidentally do it by saying something like passing in 10 for x by passing it in as the first argument, and then later on accidentally specifying that x equals 8. Here we get the same kind of error. So we see that we have multiple values for the argument x on line 5, and that's because here it looks like x should be 10 by virtue of the fact that we passed 10 in as the first argument, and then here it looks like x should be 8 by virtue of the fact that we specified x equals 8. Another thing to note about keyword parameters are that keyword parameters always have to be expressed after positional arguments. So I'm going to modify our code to say that x should be 10 and z should be 8, and this works just fine. But if I change the order of this to say that z equals 8, and then we pass in 10, then we're going to get a syntax error. And that's because, again, keyword arguments always have to come after any positional arguments that don't specify a keyword. So, in other words, we have to put z equals 8 after specifying that x is 10. So if I change the order here again, then we'll see that our code is fixed. Now, let's look at some questions that involve keyword arguments. So in this question, we're asked, what value will be printed for z? So we call our function f, we specify x is 2, we specify y is 5, and then we have z equals initial. And so what that means is z is going to be the value of initial. As soon as this function is declared, we can see that initial is set here, and so the value of z is going to be 7. In this question, we're asked what value will be printed for y. So we have the same function definition, so we specify initial equals 7, and then we provide default values for y, which is going to be 3, and for z, which is going to be 7. And then when we call our function f, we pass in a value for x, which is 2, and a value for z, which is 10. And so what that means is that y gets its default value, which is 3. So we should get 3 printed out for y. In this question, we're asked, what value will be printed for x? So we have the same function definition, x, y, and z. And when we call our function f, we specify that x is 2 here, but then we also specify that x is 5. And this isn't going to fly. Python is going to give us a runtime error because we tried to specify 2 different values for x, 2 and 5. So the answer here is E. In this question, we're asked, what value will be printed for z? So we have the same function definition as before, arguments x, y, and z. We specify that z's default value is going to be initial. When we define our function, the value of initial is 7, but it just so happens that we overwrite that value later on so that it's 0. But again, these default values are only evaluated when we declare the function. And when we declare this function f, initial had the value 7, and so we can just almost replace this with the value 7. And it doesn't matter that we changed initial later on, z is going to have the value 7 by default. So the answer here is B. That's all for now. Until next time. Lambda expressions are an alternative way of defining functions. So suppose that we have this function definition, and here I'm using args as a stand-in for a list of arguments. So I might have x, comma, y, comma, z. These arguments might even have default values. So I might have x equals 1, etc. And we have some return value expression. So that might be return x plus 5, or any expression that we want to return. If we have that kind of function, then we can express it using a lambda expression. This is a lambda expression. Whatever we wrote for our list of arguments here, we could transplant to our lambda expression and reuse it down here. So we could have lambda, and then our argument might be x and y. And then we say colon, and then whatever value we want to return, we can again specify in our lambda. So we might say return x plus y. And this expression has a value whose type is a function. We don't even need to give this function a name like we do when we use def. If we do want to give it a name, we can say func equals and then provide our lambda function, but we can also make it an anonymous function. In other words, a function that doesn't have a name. So let's look at some code examples. Here on line 1, we define a function f. It takes in one argument x, and it returns x minus 1. And again, this is kind of the traditional way of defining a function. If we called our function by saying print f called with 3, then we should get the value 2. If we print out the function object itself by saying print f, then we should get that this is a function named f. And if we print out the type of f by saying print the type of f, then we should get that f is a function. Now, if we wanted to write this function with an equivalent lambda expression, then we would say lambda x, which is our argument, and then we want to return x minus 1, so we just write x minus 1. Again, we don't need to add a return statement for lambda expressions. In lambda, the return is implicit. So if we print out the value of this expression, then we should see that it's a function. So in this case, it's a lambda function specifically. If I instead say LF equals this value, and if I print out LF called with 3, then we should get 2. And if I print out the type of this lambda function, then we should see that just like f, our lambda function LF is a function. So suppose that we wanted to convert this traditional function definition, called last char, into a lambda function. Then what we could do is we could say last char equals a lambda. It takes in one argument s, so lambda s, colon, and then again, remember the return is implicit with lambda, so we can just say s sub -1. And now the value of this expression is a function which is equivalent to this function. We don't necessarily need to actually give it a name, but here we chose to give it the name last char. So let's answer some multiple choice questions about lambda functions. So this question asks, if the input to this lambda function is a number, then what's returned? So here we have a lambda expression. It takes in one argument, x, and it returns -x. And so what that tells me is that if we pass in 1, we should get -1. If we pass in -10, we should get +10, etc. And so that to me is B, a number of the opposite sign, so positive numbers become negative, negative numbers become positive. So I would answer B. That's all for now. Until next time.
Welcome back. In today's lesson, you're going to learn a powerful new command for sorting. Sorting's a big deal in the computer science curriculum. In a typical computer science curriculum, you would learn several different sorting algorithms, and you'd analyze properties of those algorithms. In my first programming course, back as an undergraduate, I had to implement something called merge sort, where you take the items, you keep chopping them in half until you get to very small lists, which are already sorted. And it turns out that taking two already sorted lists and merging them together into an even bigger sorted list is something that you can do pretty easily. It goes pretty fast, and so we build up from these small sorted lists until we have the whole thing sorted. So I spent days and days in the computer lab. It was before we had personal computers, so I had to go to the computing lab, and every time I hit run, I had to wait for the mainframe to run the program and print out a stack of papers telling me how the program had run. After many hours over several days, I very proudly took a stack back home and showed all my roommates, yeah, I finally did it. It won't be so hard for you. We are not going to look at details of sorting algorithms. We're just going to use a built-in Python function. But we do want you to have a little mental model of what happens inside of a sorting algorithm, because it's going to help you to figure out how to invoke it well. And we've given you these great videos from Sapientia University illustrating sorting algorithms using Hungarian folk dances. You'll watch a couple alternative Hungarian dances showing different sorting algorithms. Don't worry about the details of the algorithms, but do notice something that they have in common. They always involve a bunch of pairwise comparisons, which are interactions between a pair of dancers. Two dancers will look at each other. They're each wearing a number, and they look at their numbers, and they do a little dancing, and the one with the higher number always ends up on the right at the end of that interaction. After they've done a whole bunch of these pairwise comparisons, the dancers are in order by their numbers. So again, the particular sorting algorithm is not our focus here. We're just going to call a function that does the sorting for us, and whatever sequence we give it comes back sorted in the order we wanted. At the end of this lesson, you will be able to invoke the sorted function to sort any sequence. You'll be able to specify either low to high order or high to low using the reverse parameter. You'll be able to specify a property to sort by using a key function. And in a later lesson, you'll learn some more advanced sorting things. So we'll see you at the end. Let's get started. Python provides two ways to sort a sequence: the .sort method and the function sorted. We'll start with the .sort method. It operates on a list, and it doesn't return anything, but it changes the order of items to be from lowest to highest. For example, on line 4, we first specify the list, L1, then we have the dot notation saying we're going to do a method on L1, and we're going to do the sort method, not passing any parameters to that sort. Once we've executed that on line 4, when we get to line 5 and print, by magic, L1 is going to have its items sorted from lowest to highest, -2, then 1, then 3, and so on. So let's run that. And sure enough, we get them sorted based on the print statement on line 5. On line 6, we're doing the same thing, except instead of sorting the first list, we're sorting L2, which has 3 strings in it: cherry, apple, and blueberry. What does it mean for one string to be smaller than the next? Well, we use dictionary order or alphabetic order. So apple begins with A, blueberry begins with B, so apple comes before blueberry, and we get the list apple, blueberry, cherry. Our second option is the sorted function. It sorts the items in exactly the same order, but there are a few things that are different about this way of telling Python to sort. First, of course, is that we're using the function syntax instead of the method syntax. So no period. The sequence that's going to be sorted, we pass in as a parameter to the sorted function, and we're going to get a value back. That's our second difference. We get a value back, and we can either assign that value to a variable, as we've done on line 3, or we can use it in an expression. So for example, on line 5, we're passing it directly to the print function. A third difference is that when you invoke sorted on a list, it doesn't change the original list. it produces a new list that has the same items in a different order. So when we get to line 6 and we print the original list, that original list won't be changed at all. So let's run that. And you see that we get from line 3, apple, blueberry, cherry, and the same thing from line 5. The same result of calling sorted is getting printed again on line 5. On line 6, we're asking to print whatever is the current value of L2, and that is unchanged from the original list. So notice the difference here. On lines 10 through 12, we're doing the original way. So we see from line 11 that we invoke using the dot notation, and then we don't have to pass the list as a parameter because it's being specified before the dot. When we use sort, if we then print on line 11, we see that the list L2 itself has been modified. And one other minor thing to notice here is that when we call sorted, it returns a list. When we invoke the sort method, as we do in this lower half on line 12, we don't get a value back. We just get the value none. All of the action of the dot sort method is a side effect. It changes L2, but it doesn't return anything useful. The value that we get back is just none. So that's the basics of sorting in Python. For the rest of these lessons, we'll be using the sorted function rather than the sort method. It's just safer that way. We've emphasized previously how confusing things can get when you use mutation operations, so we avoid them whenever we can. One other nice thing about the sorted method is that we can apply it to any sequence, not just to lists. We could, for example, try to sort a string rather than sorting a list. So you might wonder, what is this going to produce? And I encourage you to try to pause this and make a prediction. What will this do? Is this just going to give us apple back? Well, no, it's not going to give us apple. It's going to treat apple as a sequence of characters, A, P, P, L, and E. So it's going to give us a list of single letters, and they're going to be in alphabetic order. So we get A, E, L, P, and P. The comparable operation will fail because we can't destructively sort a string. Strings are immutable, and that's going to give us an error. The sort attribute is not available for strings. So .sort you can only do on lists, but the sorted function you can do even on immutable sequences like strings. So in general, we're going to use sorted and not sort. See you next time when we sort things from highest to lowest. Welcome back. What if we don't want to sort from the smallest item to the largest, but instead we want the reverse order? Well, that's easy. You've already seen how you can reverse a list. There's actually a reverse function, or you could do a list accumulation. But it's actually even easier than that because we can specify an optional parameter for the sorted function called reverse. That's an optional parameter. Its default value, if you don't provide a value for it, is false. But if you pass the value true in, you get the list back in the opposite order. You can see that on line number 2. In addition to saying what list we want to sort, we're also saying that the reverse parameter should get the value true. And when we do that, we'll get the things in reverse order. Cherry, blueberry, then apple. I hope I'm not making you too hungry with these examples. So this reverse equals true is just passing a parameter, the usual thing that we've seen before for functions. The actual value that we're passing in here, the word true, is just a Boolean value, if you'll recall from when we were doing Boolean values. I could change this, and instead of passing the Boolean value true, I could pass the Boolean value false, and that would say, don't give this back in reverse order. Not reversed, so we would get apple, blueberry, and cherry. Now, false is the default value for the reverse parameter. So if I leave it out entirely, I get the same thing that I would get as if I say reverse equals false. So if I don't want it reversed, I don't have to say it. If I do want it reversed, I have to say reverse equals true. And I get it in the reversed order. So that's sorting a sequence in the opposite or the reverse order. We'll see you next time when we specify a custom order for sorting based on some property of the items that are getting sorted. Welcome back. We're going to learn something that's extremely useful and powerful, but conceptually a bit tricky. So hang in there on this one. Once you get it, you're going to think, wow, this is really cool. At least I do. So let's say we have a list of numbers, like L1 created on line 1, and we want to sort them on some property, like their absolute value. So from line 9, we're printing out the absolute value of 3, which is just 3. But the absolute value of minus 119 is 119. And on lines 12 and 13, we're just going through each of the items in the list, and we're outputting their absolute value. So we get 1, 7, 4. Instead of minus 2, we get its absolute value, which is 2, and finally 3. Now suppose we want to sort L1 based on the absolute value. We can just tell the sorted function to use absolute value as the property that we want to sort by. The way we do that is we use this other optional parameter called key. So here's another optional parameter, just like we had reverse in the previous video. Here we've got key, and we can specify a value. We're going to specify absolute, and that tells the sorted function to sort by the absolute value. Here you can see that instead of having minus 2 first, minus 2 is coming after 1 because its absolute value is bigger. We've printed out the sorted version of L2. We can also do it in reverse order by combining the use of reverse equals true with key equals absolute, and we've got that here. Now that all seems pretty straightforward until you start to really think about what's going on. The thing that we're passing as a value for the key parameter is the value of the variable absolute. That value is a function. So we're passing a function, absolute, to another function, sorted. I hope your first reaction to that is, like, it should blow your mind, like, huh? We're passing a function to a function? So, yeah, that's really weird. But eventually you're going to say, wow, that's really powerful. So to make sense of this, we need to have a little mental model, a way to think about what's going on inside the sorted function. We're passing it in this function, and what is it doing with that function? Well, what it's doing is, before it starts comparing any of the items to each other, remember comparisons, that's like the pairs of dancers comparing their numbers to each other. So before it does any of those comparisons, the sorted function uses the function that you pass in, absolute, and it uses that to determine numbers to assign to each of those dancers. That is, behind the scenes, when you call sorted, Sorted is going to call the function that you provide, and it's going to call it once for each of the items in the sequence. It's going to do that to determine some property of that item, like its absolute value. It's going to write it down on a little post-it note that the item carries around. And then the sorted function does all the kinds of comparisons between the items, but the comparison's always between the values that are on those post-it notes. So for example, how is this working? We've got this sequence 1, 7, 4, -2, and 3. Before we do any of those comparisons between pairs of items, we're going to run our function, absolute, on each of the items in turn, and we're going to annotate the item with a little post-it note. So we're going to have a post-it note for 1 that its absolute value is 1, and for 7 that its absolute value is 7, for 4 that its absolute value is 4. Those are kind of uninteresting, but for -2 we get that the absolute value is 2, and that's going to change things a bit. Then we go and do these pairwise comparisons, 1 against 7, and 7 against 4, and 7 against -2, and all of that. There's a whole bunch of those that happen behind the scenes in the sorted function, but whenever it's doing a comparison, it uses the post-it notes to determine the order. So we end up with 1, and then -2, and then 3, 4, and 7. And the reason we end up with -2 coming after 1 is because we had the comparisons based on their post-it notes. 1 had the 1, but -2 had 2. So -2 with its post-it note of 2 ends up coming after 1. So if you think of that as being the process that's going on, you invoke the sorted function calls your function, like absolute, and it calls it once on each of the items in the sequence. I'm going to prove to you that that really is what's going on. The way I'm going to prove that is I've modified the absolute function here just a little bit by having it print something out. Just added this thing on line 4. So every time the absolute function gets invoked, we're going to print something out. So on line 10, we're saying to print something, then we call the sorted function, and then we print something to say, hey, we're done with sorting. Well, you'll see that line 10 generates that, and line 12's print statement saying that we're done is there. Then everything in between is stuff that's happening because of calls to absolute that happened during the execution of line 11. So we pass in the value absolute to the sorted function. We never actually say invoke the absolute function. We never do that, but inside the execution of the sorted function, it is calling absolute. And it's calling it 1, 2, 3, 4, 5 times, once for each of the 5 items in the list. And you can see it's calling it for the value 1, for the value 7, 4, -2, and 3. So that's what's going on behind the scenes when the sorted function is executing, just so it can get the right numbers onto the post-it notes so that it can use those for doing all the comparisons that lead to sorting of the items. So the thing that you pass in for the key parameter has to be a function. So often we'll call it the key function. It has to be a function, like absolute is here. It's a function. It has to be a function that takes one input. That input is going to be one of the items at a time from the list. And it has to return some value that's going to go on the post-it note, some property of the item. so typically a number. Now I just want to mention one thing here about passing in a function. We can either pass a function by name, as we did originally with this. We just say the absolute function, or we can pass in a lambda expression. Remember from a previous lesson that lambda expressions are expressions that produce anonymous functions. So instead of specifying absolute here, we could specify a lambda expression. So this is a lambda expression. This whole expression evaluates to a function object. That function takes one input x and returns as its value whatever this expression returns. Now, if you write this like this, it might look a little silly to an experienced programmer because really this lambda expression is returning a function that does exactly the same thing that absolute does. But you might still want to do that just if it makes it clearer for you. This is a conceptually challenging thing, this idea of passing in a function for the key parameter. And I find a lot of students really, they just understand it better this way, where the lambda reminds them that they're producing a function, and when they just see key equals absolute, it doesn't quite click that absolute is referring to a function object. So if this helps you, you're welcome to do it this way. There are other places where we'll have other lambda expressions which make even more sense, and we'll see that in a later lesson. So to summarize, if you want to sort a sequence based on some property of the items, call sorted and pass a value for the key parameter. The value for the key parameter has to be a function. That function takes one item as input and returns a value to write on the post-it note, a property of the item. The value for the key parameter can either be the name of a function, like absolute, or a lambda expression, like I've shown on line 9 here. So play around with this a little, do some exercises, keep trying it until it makes sense, and then you'll be able to sort anything, anytime. See you next time. Congratulations, rah rah! You've learned how to get Python to sort sequences for you. The sorted function handles all the details. You just have to specify the desired sort order. So you should now be able to invoke the sorted function to sort any sequence. You should be able to specify low to high or high to low sorting using the reverse parameter, and you should be able to specify a property to sort by using a key function. It's joke time. I'm sure you've heard some rags to riches stories about the guy who started out working in the company mailroom and eventually became the CEO. Well, this one has a little twist. It's Jerry's first day at the company, and he's assigned to the mailroom. He's given the task, sort the incoming mail. And Jerry sorted the letters so fast that his motions were literally a blur. His supervisor was very impressed. At the end of the day, the supervisor approached Jerry and says, "I just want you to know that I'm very pleased with the job you did today. You're one of the fastest workers we've ever had." "Oh, thank you, sir," said Jerry. He's beaming. "And tomorrow, I'll try to do even better." "Better? How is that even possible?" Jerry replied, "Tomorrow, I'm going to read the addresses." We'll see you next time when we sort dictionaries and learn how to break ties. Hi, glad to have you back for a little more in-depth look at sorting. We're going to look at sorting dictionaries, which can be a little confusing even though it follows the same mechanics that you learned in the previous lesson. We're also going to look at how to break ties in the primary sort order with a secondary sort order. At the end of this lesson, you should be able to sort a dictionary's keys based on their values, or some property of their values. And you should be able to break ties by having the key function return a tuple. Bye for now. Welcome back. One sorting task that comes up frequently but's a little tricky is sorting a dictionary. The way we sort a dictionary is to sort its keys. After that, we can iterate through the keys and look up values as we need to. So remember this code? You've seen something like it before, maybe with a slightly different list. We've just got a list with a bunch of items. Some of them are repeat, and we're creating a dictionary that counts for every item, for every distinct possible value in the list. How many times does it come up in the list? So A comes up once, twice. So at the end, in our dictionary D, we're going to have the value 2 associated with the key A. And then on lines 9 and 10, we're just printing out the values from that list. So E appears twice, F appears once, A appears 2 times, as I just manually counted, and so on. Notice that the keys, E, F, A, B, C, and so on, they appear not in any special order. And that's just the way dictionaries work. When you ask for the keys, you get all the keys back, but there's no promise made about what order they'll appear in. Suppose I cared about the order, and I really wanted to say, A appears 1 times, B appears twice, and so on. The way to do that is going to be on line 9 to sort the keys before doing the iteration. So let's suppose that instead of just asking for the keys, I pass those keys into the sorted function. Now I'm going to get the results in alphabetic order. A appears 2 times, B appears 2 times, and so on. Well, that's all well and good. How about if we wanted to sort based on the counts instead? So we really want D to get printed out first because it appeared the most times. And after that, we'll get the things that appeared only twice. Now, we can specify a property of these keys that we want to use for sorting. And there's a little confusion that's going to go on here because we're using the word key in 2 different ways. We use the word key to refer to a key in a dictionary. Like in this dictionary, D, we have the letter capital A as a key and capital B as a key and so on. But then we have a second use of the word key, which is the parameter name in the sorted function. So if we want to say sort these keys based on some property of them, we say key equals, and we pass in a function here. So these are just 2 different meanings of the word key, and you got to keep them separated. So remember, the key function is going to take one list item as an input. In our case, we have a list of all the keys, A, B, C, D, E, F, and so on. And so that's what we're going to have as one input. And I'm going to call my function, the parameter for this function, K, just to remind me that the thing that's getting passed into it is one key from the dictionary, like the letter A or the letter F. I'm choosing the parameter name K to remind me of that. And then we're going to return a property of that key. And the property we want is, what is the value associated with that key in the dictionary D? So if I have the key C, what I want to do is get the value 1, and I want to use that for the sort order. For D, I want to use 4. The way I can do that is I refer to D square bracket K. Just look up for the current key, what is its value in the dictionary, and I get, if the current key is C, I'll get 1, and if the current key is D, I'll get 4. And this is really all I need to do in order to resort this output in the way that I want it. Let me just clear those markings for you. So now we have D appearing at the end because we're going lowest to highest, the items that occur least frequently, to the ones that occur most frequently. If I wanted to do it in the reverse order, I just do. If I wanted to do it in the reverse order, I just use it reverse equals true like we've done before. Now D will get printed out first. So the things to remember here are we're not doing anything new with sorting. There's no new mechanics here. We're just passing in a function for the key parameter. But we have perhaps a little bit of a confusing function. This function is taking one key from the dictionary as its input and returning a property of that key, the lookup of its value in the dictionary D. So we have key as in a key from the dictionary. That's our letter K. We've chosen to remind us that we're dealing with a dictionary key. And then we have the parameter name key for the sorted function. One other thing I want to point out is that when we tell the sorted function to sort the keys, there's a shorthand we can use. You may recall we've said before that any time a list is expected, there's some place in the code where the Python interpreter is expecting a list. If you provide a dictionary, it will automatically grab all of the keys as the list. So this is equivalent. We can either say d.keys or we can just say D. Because we're passing them to sorted, if we pass the dictionary, it automatically figures out that we want to sort the keys. So this is sorting a dictionary's keys based on their values. There are several useful exercises at the bottom of the page in the textbook that I encourage you to work through in order to solidify your understanding. We'll see you next time. Welcome back. What if we really want to control the sort order, specifying how to break ties on the primary property we're using for sorting? The answer is that we take advantage of Python's built-in sort order for tuples. So take a look at this code. I have a list containing 5 tuples. Each tuple has 3 items in it. The first tuple has A, 3, and 2. The second tuple has C, 1, and 4, and so on. On line 6, I am going to sort those tuples. So we're still going to get a list of 5 tuples, and then we're just going to print each of them with an iteration. What order do you think they're going to come out in? Is it just going to do them in the original order because it doesn't know how to sort tuples? Is it going to put all of the A's first? So we'll get this one, and then this one, and then the B, and then the 2 C's. Is it going to do some random order? What's it going to do? Well, let's see. What it's going to do is put the A's first, and then the B's, and then the C's. So when you sort tuples, you're really sorting by the first element in those tuples. But there's more. We have a built-in tie-breaking mechanism with tuple sorting. Here, the first values were both A, so it went on to the second value, and 2 comes before 3. There was only one B, so there was no tie-breaking that needed to happen. But between the 2 C's, those are equal, so it goes on to the second element. If those are equal, it goes on to compare the third elements, and it would even do fourth and fifth, as many as you had elements in the tuples. So when it compares two tuples, it first compares their first elements. If one of them is smaller, then that whole tuple is smaller. But if they're equal, it goes on to compare the second elements of the tuples, and then the third elements, and so on. So that's going to turn out to be useful for us when we try to control a sort order for breaking ties, even when we're not sorting things that are tuples. Suppose we had really duplicate items. So we had another A, 3, 2. That's exactly the same as the first element. In that case, it's just going to put both of them in there, one after the other. So we've got both of the A32s showing up. It's never going to collapse them. If you have 6 elements to start with and you sort the list, you're always going to end up with 6 elements at the end, even if 2 of them are identical. All right, so that's sorting tuples. We're going to take advantage of the Python sort order for tuples in order to be able to specify, fine-grained control on our sort orders for other things, using tuples to create a tie-breaking mechanism. The way we're going to make this tie-breaking mechanism is that we're going to make our key function, as always, take one item as input, and it's supposed to return a property of the item, but instead of returning one property of the item, we're going to return a tuple containing 2 properties of the item. So here's an example. We've got a list of fruit names, and we're going to sort them. And the property that we're going to use to sort them is defined by this lambda expression. It takes as its input one fruit name, and it returns as its output a property. But in this case, it's 2 properties as a tuple. The first one is the length of the fruit name, how long is the word, and the other is the fruit name itself. So this is going to produce for peach a tuple 5, peach. For kiwi, it's going to produce 4, kiwi. And remember this idea that the key function is sort of producing a post-it note that's associated with the item. So peach has associated with it this tuple, and kiwi has associated with it this tuple. When sorted is going to decide what order they should go in, it's sorting them based on these post-it notes, these tuples. So 4 kiwi is going to go before 5 peach because the tuple ordering says look at the first element of the tuple first. However, when it comes along and sees 4, pear, it's going to have a tie when it compares 4 with 4, and it's going to then use alphabetic ordering as the secondary sort order to break the ties. So we'll get as our output we get the 4-letter fruits first, kiwi and pear, and then the 5-letter fruits, apple, mango, and peach, and those are in alphabetic order. Apple before mango, M before P, mango before peach. What if we want to have the long words first? This is just our standard mechanism with the sorted function. We can add the reverse equals true parameter. And now we'll get blueberry to show up first. That's all fine, except it's completely reversed the sort order from what we had before. So now we have peach before mango before apple. Those are all the 5-letter words, and we now have them in reverse alphabetic order in addition to reversing the long words to short words. What if we wanted to have longest words first, but break ties with alphabetic order rather than reverse alphabetic order? This starts to get pretty tricky. One solution that's available to us is a little trick. Instead of using reverse equals true to reverse our sort order, which will make it so that we reverse both the primary and the secondary property. I'm going to try to just reverse the primary property, and there's a trick I can use for numeric properties, like the length of the fruit name. If I just make all of them be negative values, so blueberry is now going to be -9 and kiwi is going to be -4. -9 is less than -4, and so I'm going to get the longer ones to come first. But I haven't reversed everything, so my secondary sort order is still going to be from lowest to highest, which will be alphabetic. So I've still got blueberry first, but I now have apple before mango before peach in alphabetic order. Now, that trick only works if we have a numeric property. If you had two alphabetic properties and you wanted to do reverse on one and not on the other, it would be harder, and I don't have an easy solution for you. So summarizing, if you want to specify a tie-breaking property, have your key function return a tuple. Like key functions everywhere, they always take one item from the sequence as input, but now it's going to return a tuple, where the first element of the tuple is the primary property to sort by, the next element is the secondary property to sort by, and you could even have more elements in the tuple. We also saw that if you just want to reverse order for one of the properties but not the others, instead of using reverse equals true, you can make the key function return the negative of all the numbers. See you next time. Glad to have you back. Here's a little way of the programmer advice on when to use a lambda expression and when to use a named function for your key parameter when sorting. Basically, my rule of thumb is if the lambda expression is short and simple, so that it's pretty easy to understand what it's doing, use the lambda expression. And as soon as it gets too complex, refer to a named function instead and give it a good name that describes the property you're trying to sort by. For example, here's one that's just at the outer limits of what I'd consider simple enough to put in a lambda expression. We have a dictionary called states. It's got as its keys the names of states in the United States, Minnesota, Michigan, and Washington, and the value associated with each state, with each key, is a list of city names. St. Paul, Minneapolis, St. Cloud, Stillwater for Minnesota, Ann Arbor, Traverse City, and so on for Michigan. Now we want to sort the keys based on some property of their values. So we have a generic structure where we have a dictionary called states, and we're going to sort its keys. We just asked to sort the dictionary, but that always means we'll get to sort the keys. And our key function is going to take one item from that list as an input, and it's going to look up some property. In fact, it's going to look up that state in the states dictionary. But in this case, we're not just trying to get the whole list as the value associated with Minnesota. We're trying to get some property of that list. And in this case, we're taking square bracket 0. So we're taking square bracket 0, so that would get us St. Paul. And we're passing it to the len function, so that's going to give us 8. And for Michigan, we would take the list, that's states, square bracket state, gets us the whole list of cities. We take square bracket 0 from that, that'll get us the city of Ann Arbor, and we'll pass that to the len function, so we'll get 1, 2, 3, 4, 5, 6, 7, 8, 9. Ann Arbor has 9 letters. And similarly for Washington, we'll get the length of Seattle, which is 7 letters. So when we sort this, we should get a list of the states, Minnesota, Michigan, and Washington, but we should get them in the order Washington first because its first city has a shorter name. And sure enough, we get Washington, and then Minnesota, and then Michigan. So that's great when the property we wanted was the length of the first city name. And as I said, I think this is sort of just at the outer limits of what's understandable in a lambda expression. This got to be kind of complicated. It worked pretty well to understand it because state square bracket state is sort of a chunk, a pattern that we've seen before. We're taking a dictionary key and we're looking up its value in the dictionary. If you think of that as a little chunk as, oh, that's the value of the state in the dictionary, then we can just parse the square bracket 0 to say, oh, take the first element of the list and pass that to the len function. Anything much more complicated than this, I think, would be pretty hard to read as a lambda expression. Well, let's think about one of those harder things. Suppose that we wanted to take a different property. For each state, we want to find the number of cities in its city list that begin with the letter S. We want to sort in that order. So, okay, what does that property sound like? The number of states that begin with the letter S. Number of states, that sounds like it's going to be a count accumulation. And only those that begin with the letter S, that sounds like we're going to need to filter as we count. So it's a count and filter accumulation. It's not too hard to write it as a function, but it would be pretty hard to write just as a lambda expression. So I'm going to write a function. I'm going to call it S cities count. And it's going to take as an input a cities list. And what it's going to produce as an output is a count of how many cities begin with a capital S. Well, this is a count, filter, and accumulation, so I'm going to say count equals 0 for city in cities list if the first letter of city is S, then increment our counter by 1. When we finish the iteration, CT will have the total number of cities that began with S. So we'll return CT. Now, how am I going to use that? The key function is going to take one state as input. And I wrote this cities count to do our accumulation as though it's taking a cities list. So I can't just say key equals S cities count. That's not going to work because the key function has to take one state as an input, and my key function is taking a list of cities as an input. So this is going to be a little bit of a hybrid. I'm going to take one state as an input. I'm going to look it up to get the cities list. So that's sort of our canonical way of sorting a dictionary by its values, is we look up that key, look up the key state in the state's dictionary, but that's going to give me a cities list, and I'm going to pass that to my new function. Let's see, when you write that much code, the chances of running without an error aren't very good. Let's see if I happen to get lucky. Wow, I did. Okay, so we got Michigan first, and then Washington, and then Minnesota. So hopefully if we go look at the cities list, we'll see that Minnesota is the one that has a lot of cities beginning with S. And sure enough, it does. Washington has St. Paul for 1, St. Cloud for 2, and Stillwater for 3. So it had 3. Washington had Seattle for just 1, and Michigan had 0. So sure enough, we got these in order of the number of cities that begin with the letter S. So let's review what we did here again. We made a helper function, a named function called cities count, that did our thing that was a little too complicated to put into the lambda expression. And we passed some property of our key, the list of cities in that state, we pass that as an input to this helper function sCitiesCount. Now it's actually possible to not use a lambda expression here at all and just refer to a named function. But we would have to make our function then take as input not the cities list, but the state name. So I'm going to do a version of that. I'm going to call it sCitiesCount for state. And it's going to take a state name as its input. And it'll make the cities list equal the lookup of the state in the state's dictionary. And then everything else can be the same as before. If I do that, I can say that my key function is just sCitiesCount for state. That time I wasn't so lucky. So this is always instructive. Let's look at this error message. It says syntax error EOF in multi-line statement on line 19. Now EOF might be a little confusing. It's an acronym. E stands for end, O is of, F is file, end of file. Basically it means it got to the end of the program. It was sort of in the middle of trying to parse something. And it's saying line 19, so I always like to go back and look at the first thing before that. Here's line 17, and sure enough, I am missing a closing parenthesis. So it was kind of waiting around, expecting there to be another closing parenthesis, and it didn't find it, and so it got an error. So let's run now. And sure enough, that works exactly the same as the original. Now, I actually prefer the original over this second one, even though line 17 now looks very clean. We just say key equals this function name. But I find that the previous version, and we can use our scrubber to go back to it. Let's see. Yeah, this one, where we had key equals lambda of state, sCitiesCount of state square bracket state. The lambda expression is more complicated here, but the lookup of one key in the dictionary is just a very common idiom when we are sorting the keys from a dictionary. So that's a little advice on when to use lambda expressions versus named functions. My basic advice is, if a lambda expression is simple enough, do it that way. And when it gets too complicated to read or write, then it's time to use a named function to move some things out into another function that you can give a good name for. We'll see you next time. Congratulations, now you really know how to sort. Simple sorts, complex sorts, all sorts of sorts. You can sort dictionary keys based on some property of their values. You can break ties by having the key function return a tuple. You can use lambda expressions. You can use named functions. You are a pro at sorting. Now, in the intro to this week, I made a big deal out of saying we're not going to go into details of which sorting algorithm gets used and how long it takes it to run. So instead of a straight-up joke, let me give you a little programmer's humor, a sorting algorithm that runs really slowly. It's called BOGO sort, and it works by trial and error. Take the items, shuffle them, just at random into some random order, and check if they happen to be sorted. If they are, we're done. Otherwise, try again. Shuffle, see if they're sorted. Keep going until you get a lucky shuffle. Remarkably, the code for this in Python is short. In the random module, there's a built-in function called shuffle, and I wrote the function to check if a list is in order in 5 lines, and another 4 for the trial and error while loop. Now, here's the full code. Of course, Because you do a random shuffle every time, it takes a random amount of time to finish, but as you can imagine, this is not a fast way to do sorting. If you got a bunch of items and you just shuffle them, the chances that it's going to be sorted aren't very good. I just ran it once on a list of 10 items and it took 68 seconds to complete. I didn't dare to try it with 11 items. By contrast, Python's built-in sorted function was able to sort 1,000,000 items in just over half a second. Now you have a party trick. Ask your friends who've taken some computer science courses some time ago to try to remember the slowest sorting algorithm they studied. They'll have fun recalling bubble sort and insertion sort and trying to decide which one is slower, and then you can regale them with BOGO sort. You'll be the life of the party. Trust me. See you next time.
Hello and welcome to Course 2 and your end of course project. In this project, you'll be building a program in a few steps to perform what's called a sentiment analysis. Programs like these are widely used in a bunch of different companies and different situations. And in this case, you'll be working with Twitter data, although it's fake Twitter data. You will eventually make a CSV file and use that to produce a graph of your results, which is a super useful way to visualize data and share results of programs you build with other people. Then you'd be able to build a program like this one to use real Twitter data, which we can't use in this particular case. In order to build this analysis in your eventual CSV file, we're going to take you through a series of steps to build different functions in order for you to put together this complete program. As you proceed through the program, you should focus on individual steps one by one and make sure that you understand the instructions for each step before you move forward to writing the code. You should always focus on one step at a time because thinking about multiple steps in your program can often get overwhelming and can confuse you about what code needs to happen first and what should happen later. So make sure you focus on individual instructions for one step at a time. Build your plan, and translate that into code as you work through the project. As you think about each step that you have to work through, you should think carefully about what you know about functions. What is the input for each function? What is its return value? And what does each function have to do after the input and before it returns its final output? As you work on each function, you'll be able to put them together to build the full project. Remember also that in each step, you may need to copy some work you have done earlier into the next step to come up with a chart like this. You'll want to make sure that as you work on each concept, you isolate what you have to do without focusing on earlier pieces, and focus on the examples from the course that will be useful to you for the project. For example, function definition, advanced functions, and dealing with files, since you're creating a file in order to visualize your data here. I also think that this project is a particularly exciting way to think about how you can apply these concepts to things you might want to do in real life, so to speak, understanding different things about how programs can apply to you. So good luck and have fun.